about that. Are those, I see those videos up on the NCAR YouTube page. Are those going to stay there? So
they will.
Okay, so we could share that.
Fantastic.
It won't disappear. Great.
And I think you can get, it's not hard to get permission. There we go. It's not hard to get permission to do this. You just have to like arrange with YouTube as a verified organization to be able to do it or something. So there's some arrangement we have, and then I'm added to their accounts so that I can do it automatically through my Zoom. They did that. That's all they had to do for me. So there's the YouTube link. It is funny. There's a 10-second delay though.
Yeah.
Well, that way we can beep it when somebody says something really inappropriate.
It's like scientifically controversial.
Yeah.
Aerosols have no effect. I'm a little miffed at the AMS because at the moment they reckon they're going to either do entirely in person or entirely remote for the annual meeting, and seeing how easy it is to stream to YouTube, I'm really surprised they couldn't find something to do, but I think it's got to do with their wedding with Convex, as in Convex doesn't have the capability to stream.
I don't know if AGU has said what they're doing. I think they've said it's going to be in person, but they haven't said how much is not going to be in person. So
yeah, AMS is, I mean, last meeting we had, they're quite comfortable with the topical sessions. It's the big sessions they're really worried about, the ones that normally have people queuing in the aisle.
So Danny's coming in, so we're still waiting on G-Win.
There's G-Win.
Okay.
Hi.
Good morning.
There we go. Okay. Well.
Hey. Hi.
Good, very early morning, G-Win.
Sorry, I was too early.
Oh yeah.
Okay. Anyway, so Michael, you said you want us to share slides?
If you guys can show those 2 slides I sent in your introduction, that would be great.
Yeah, I'll open it and let me share.
And then yeah, we're just waiting for Jingyi.
Okay. Jingyi replied the email. So
yeah.
I think she should. It's just too early here. Everything just a little bit slowly.
I understand.
Yeah. But
All right,
maybe
should we let everybody else in?
There's Jingyi.
Okay.
And then Andrew can make her co-host.
I'll make her co-host, and then we'll let everybody else in.
That makes it much simpler.
Okay, here we go.
You guys can see the screen, right?
Yeah, I'm gonna mute it. I'm gonna mute everybody, and then you can the co-hosts can all unmute themselves.
Yeah.
Mute. Okay. Okay, I'm unmuted. Can you guys hear me now?
Yes.
We can.
Okay, good. I think let's get started. Yeah, welcome to the session, everyone. We've had some great sessions and discussion in the past 3 days, and today is the final day of the workshop. So we have 2 sessions. The first one starts from the errors on the cloud studies from regions like Monsoon and Amazon, and then followed by a tracer focused session. For the tracer focused session, Mark, I want to share this highlight some tracer related sessions in the coming meetings. For example, this is the conference on Arizona climate interactions in MS meeting, and then the other session is at the air quality. This is which meeting? Oh yeah, 20. This both are MS meetings, I think.
Yes, that's correct, Jiwen.
Great. So it's 22nd, the joint conference on the applications of aerosol meteorology. So hope you guys can attend, and we'll also have more Trason stuff coming. There's Trason town hall, ARM Trason short course. I think ARM SR meeting will also have a Trason related session. Do we have it, Mac? In the SRPM meeting?
We are not having a tracer related session because we have our monthly calls that are basically breakout sessions.
Okay.
But there will be plenty of presence of the tracer campaign and ACPC at the ARM meeting.
Yes. Okay, so here is the nice photo taken yesterday, and it's I think we have lots of participants in there. That's great. I look forward to the graduation discussion today. Scott, did you have anything to add?
Just briefly, I want to say that while that's a nice photo, Joanne, I do remember so very fondly getting ready for that photo in Nanjing, and how much I miss actually seeing everyone in person, but also how much I enjoyed the sessions yesterday and actually listening to some of the great science being done and getting very excited for thinking about what we can do in Tracer to really get at the observations that we need there. I really enjoyed the conversation and having enough time for conversation at the end. I really want to encourage our earlier career scientists who are calling in, our postdocs, our PhD students, if they feel comfortable, get involved. I'm sure there were more questions than that folks had that were actually not asked. So please feel free to use the chat if you don't feel comfortable raising your hand and asking a question in person, and really add to the questions and discussions during the end of the sessions today. So thank you very much again to Minghua and all the organizers for this. It's a fantastic workshop.
Okay, maybe I'll introduce the today's session one's co-hosts. And usually we have 4 people help running each session, so we thank them. And today for the session 1, they are Ji Chen, Mark Jason, Jessie Hu, and Yun Wang. I hand over to Jingyi. Jingyi?
Okay, can you hear me?
Yes.
Okay, let me share my screen. Now I think you can see my screen. Let me move this. Okay.
Yes, looks good.
How to move this part to somewhere else? Maybe I'll put it this back. Yeah.
Okay, go ahead.
Okay, the first speaker is the Tianmen Chen from the Chinese Academy of Meteorological Sciences, and she will present the potential impact of aerosols on convective clouds in the eastern China. Tianmen, please take it away.
Hello, everyone. Hi. Can you hear me?
Yes, I can hear you.
Okay. Thank you for letting me have the opportunity to introduce my work here. And my talk today is about the potential impacts of aerosol on convective clouds over different terrain types. This work is under the guidance of Professor Lee, and also Ralph and Danny have offered a lot of help. Next, please. Yeah.
Oh, sorry.
This one. We know that the aerosol is still the most uncertain factor in the climate, and topography is a very important factor that can influence convective clouds. And there is always strong diurnal cycle dynamic and surface forcings. Many modeling studies has found that with aerosol concentration increases, changes of convective clouds may vary due to the co-action of topography and aerosol effect. But there haven't been a lot of observational studies, so we choose to look at these problems about how this topography impact aerosol convective clouds relationship. Next, please. And to achieve this goal, we first developed a method to identify convective clouds with geostationary satellite. And then we did statistical analysis to see convective cloud fraction in polluted and clean environment. And at last, we show some differences of aerosol convective cloud relationship over different terrains. And next, please. And as Eastern China has faced with relatively severe air pollution in the past decades, and the topography conditions is very complex, it is a good place for our study. And we use Himawari 8 level 1 geostationary satellite data to identify convective clouds. And by combining texture analysis, k-means clustering, and thresholding, we developed a convective cloud identification method. And to save time, I just skip the details here. Next, please. And the flow chart of the method is shown here. By inputting texture, reflectance, and brightness temperature into k-means clustering and adding filters, we finally get the convective cloud mask. And next, please. Next, please. Yeah, we have validated the result using modest cloud mask. We choose 2 examples here. The same with many convective clouds and other with sparse convective clouds. And we can find that identified convective clouds generally matches the modest cloud mask. And we can capture most of the convective clouds in the image. So our method is capable of capturing, identifying convective clouds. And so next, please. We just classify polluted and clean environment using the surface measurement of PM2.5. We use the top and bottom quarter of the PM2.5 distribution of each side as the thresholds of polluted and clean conditions, and aggregated them into the grids. And if the clouds locates in the polluted grid, then it is a polluted convective cloud, and if it's located in the clean grid, and it is seen as the clean convective clouds. So next, please. Next, please. By comparing the convective cloud fraction in polluted and clean environment during different time of day, here we use polluted convective cloud fraction minus the clean ones. And we can see from the upper figure that polluted convective cloud fraction is generally higher in the morning but lower in the afternoon. But over mountain areas in the northwest and over cities in the black circles, the convective clouds are always invigораted in a polluted environment. And also we found a robust relationship between aerosol and convective clouds. That is, the CCF first increase, then decrease with aerosol loading. And there is a slight shape change in the moving mean curves compared with the daily trend. The tipping point moved to smaller PM 2.5 values in the afternoon. We think this could have resulted in the patterns in the upper figure, and the shape changes of the curve might be related to the meteorological conditions, meteorological changes during the day. And the next, please.
Yeah, I believe there is some delay in the slide showing here.
All right. We also see the polluted and clean convective cloud fraction over different terrain heights, and can find that there is more convective cloud before noontime and less after, which is similar to the previous figure. And to reduce the impacts of diurnal variations, CCFs are normalized by polluted and clean cases respectively. And we can see that over higher terrains, there is more convective clouds found under polluted conditions, which means that higher terrains are more sensible to form convective clouds in a polluted environment. And so this is also consistent with the previous figure that over higher terrains, the CCFs are always higher during the day. And next, please.
1 more minute, please.
Oh, okay. And yeah, as we know that Eastern China shows a steppe-like landscape, and we classify different topography with terrain heights, we can find that the relationship between aerosol and convective clouds is robust over different terrains. But the tipping point at our different before the turning dome, we can find that the higher terrains show higher convective cloud fraction, whereas after the turning dome, the pattern reverses. This is potentially because that the surface heating and stability over higher terrains is more favorable to form convective clouds, and which enhances the aerosol microphysical effect, while over lower terrains, the moisture condition is more conductive that can potentially overtake the cloud suppression by aerosol radiative effect. Next, please. And we can also to see whether the inference is right, and we have examined the relationship by stratifying thermodynamic, dynamic, and moisture conditions. The factors including cape surface potential temperature, vertical velocity, relative humidity, and surface specific humidity. And the red lines mark the mean tipping point of the relationship, and we can find that the convective clouds fraction always shows a first increase and then decreasing trend, and aerosol with aerosol regardless of meteorological conditions. And as the meteorological factors changes during the day and over different terrains, we can find that the larger cape, stronger surface heating, and vertical velocity may lead to smaller value of tipping point, while a larger relative humidity is likely to lead to larger values of tipping point, which may support the idea that the tipping point changes are related to meteorological conditions. And next, please. This is the end. And I just leave the summary here. We just provide observational patterns here and think further modeling studies and campaign data will be helpful to review the mechanisms behind this phenomena. And that's it. Thank you. More details can be found in the paper in the next slide. And that's it. Thank you.
Okay, thank you very much. I think in the interest of time, we're going to have to move on, but I see there's several questions in the chat there. Tunmeng, if you could take a look at those and try to answer them in the chat.
Okay.
Okay, and Jingyi, this next talk is the one that there's the recording on, right?
Yes.
Yeah.
Jingyi, did you have the file open, the recorded one?
I have the file open, but and I can see there
No,
is
the recorded video. Yeah, Manach, they had a hurricane, destroy the internet connectivity, so he cannot present. He has a video. I'm open the video. I can share if.
Oh, okay. I don't have the video, so I stopped sharing now.
Let me try. If it doesn't work, we may move on. Let me try. You guys see my screen?
Yes.
And let me play the video.
That's playing.
Can you guys hear okay?
I don't think he started speaking yet. So this.
Oh, okay. Not yet. Yes. Let me move a little bit.
Good afternoon to all of you. Myself,
Okay.
Manoj. I did this work at the Earth System Science Interdisciplinary Center, University of Maryland, USA. The topic of today's talk is contrasting aerosol effects in triggering deep convection results from GVAX campaign. The science objective is to assess the relative role of competing aerosol-induced thermodynamic and microphysical effects in triggering deep convection over the endogangetic plane using observational data and modeling framework. The basic methodology is likewise as the following. The composites of aerosol, cloud, and meteorological parameters during the formation of deep convective clouds, that is DCCs, under both light and heavy pollution conditions are contrasted to elucidate the aerosol effects. This is the data and study period. Location is Nainital in India. Study period is June through September 2011. Parameters are aerosol, cloud, and meteorological variables observed from field campaign and satellite data. Model is the WRF ARW. This is the box covering the study location, and this circle is the location, study location. And basically, we consider two types of events. One is DCCs under high IOD condition, that is HADCC, and DCCs under low aerosol conditions, that is LADCCs. And this is a special pattern for various aerosol and cloud parameters. You can see that AOD, COD, CTP, that is a cloud top pressure, COD ice, then CER ice, CIP, that's a cloud ice path, cloud fraction, and the aerosol index, distinguishing the aerosol from absorbing or scattering ones. You can see that there are high IOD and COD values over the northwestern part of the IGP and also around the Nainital. As evident from the previous figure, it is you can see that moderately high aerosol COD, moderately high correlation coefficient between aerosol optical depth and the cloud optical depth. And since aerosols can induce variations in the surface temperature, especially in the planetary boundary layer, we looked at the how is the temperature profiles during the HADCC cases and the LADCC cases. You can see that there are multiple inversions observed on the when low high aerosol concentrations were present, and there is a 2-degree increase in the near surface temperature during the HADCC cases. Now we just examined the thermodynamical response in the PBL and the surface evaporation. This is for the boundary layer height, and this is for the evaporation, surface evaporation. You can see that the boundary layer height is increased in the HADCC cases, and the evaporation is reduced in the higher conditions. Now, since the aerosols can alter the dynamical and thermodynamical parameters in the PBL, we basically examine one parameter called the moist static energy, which feasibly encompasses the temperature and water vapor effects. So this is the special plot for the internal energy, that is CPT, and this is for the latent energy, that is LQ in the MSE equation, and this is the sum of all the three terms, that is MSE is CPT plus GZ plus LQ, that is the sum of all these parameters. So basically from the spatial plot, it is evident that the MSE is increased over the same region where aerosols are higher. Now, as a result of the moist enhancement in the moist static energy, the lower atmosphere is conducive for convection and producing certain moisture convergence in the PBL, because if the lower atmosphere is heated up, it can induce convergence, and since there are a lot of evaporation, it can increase the moisture convergence. So during the DCC phases. Therefore, we examine the composite of vertical profiles of moisture convergence for HADCs and LADCs, and there is a considerable increase in the moisture convergence in the PBL during the HADCC cases, which favors convection. Now, the same thing is evident from enhancement in the cloud ice water path and ice water content and vertical velocity for HADCC cases. In both the cases, they are enhanced. Now, there's a corresponding increase in the total cloud ice water content, CAPE, and high cloud fraction for HADCs as evident from this figure. Now we see the possible role of aerosol indirect effect, and is there any possibility of invigoration? We assess the aerosol indirect effect using this formula. While the LADCC cases, which will be shown in the next slide, were associated with a much stronger and intermittently significant anti-Tomy effect for most of the bins, the HADCC events were marked by non-significant and negligible AIE, that is intermittent cases of Tomy and anti-Tomy effects compared to LADCCs. This is for the aerosol indirect effect for LADCC cases. From this one, it is clear that though not frequent for all the events compared to the LADCCs, the weak anti-Tomy effect hints to the possibility of a suppression of warm cloud droplet growth. This might lead to more cloud water to be lifted up, which is further evident from the vertical profile of enhanced cloud ice water content at upper levels for HADCCs in contrast to LADCCs. We wanted to test our observation with the model simulation using the WRF-ARW. This is the model setup, and this is the concentration. Basically, the extension coefficient obtained from the Calypso is converted into CCN. And this is the composite for extension coefficient for HADCC and LADCC cases. As you evident from this figure, HADCC cases is having higher aerosol concentrations. Now we see the aerosol effects on lower atmosphere in atmospheric stability in the model simulation. You can see that this is the vertical profile of potential temperature difference between the control and experiment one, and this is the d theta by dz. So a low level cooling that is around 1.7 degrees Celsius up to about 700 meter is evident in the when aerosols are more, that is in the control run. Also, the stability is higher in the control run, wherein aerosol concentration is higher. This shows the time difference of a sensible heat flux. The difference is negative over most of the entire period, implying more sensible heat in the experiment run compared to the control run. Now, if we see the spatial plot of latent energy as we did for the observation, that also supports our simulation, our hypothesis that there is enhancement in moist static energy in the control run. A confirmation of moisture convergence from model simulation is also made. Here, this is the vertical profile of all the MSC. That is a difference between the control and the experiment run. You can see that all the three parameters, that is the internal energy, latent energy, and the moist static energy are higher in the control run. And similarly, there is enhanced moisture convergence in the lower level in the control run. Similarly, the latent energy time series also, if you examine, that also shows more latent energy in the HADCC cases. So the more radiation reaching in the surface in the experiment run could induce more evaporation of moisture from the surface, thereby enhancing latent heat flux. Latent heat flux could also be increased via the lower level convergence of moisture induced by aerosol heating of lower atmosphere. And if you see the heating rate, you can see that there is a clear distinction between the heating rate for the HADCCs and the LADCCs. You can see that more than 2 degrees Celsius increment in the lower atmosphere. And finally, our conclusion is if we see if the aerosols could induce moisture convergence in the lower atmosphere, opposing the original static stability induced by enhanced aerosols, that could enhance deep convection via low-level moisture convergence, and hence there is an enhancement in the accumulated rainfall for the control run compared to the experiment run. In the experiment run, the aerosol concentrations were reduced by 4 times. That's the summary of the study. The study is taking advantage of the rich measurements collected during the atmospheric radiation measurements program. That is the GVAX program conducted in June to September 11. Although heavy loading of absorbing aerosols might stabilize the planetary boundary layer and weaken the convection, observational analysis highlight the seminal role played by aerosols in increasing the moist static energy, thus increasing the convection potential of the lower atmosphere. This moisture convergence leads to local dynamical changes that trigger greater moisture feedback and regional precipitation. Computer simulations using the WRF model also substantiate these observational findings. Thank you.
Okay, Matt. Is time okay? I think we will not have time for question.
Nope, I think we need to move along, but I think if you have questions on Manoj's talk, Jianxing can probably answer some of those. So put them in the chat if you do have a question. And yeah, with that,
Okay.
I think we can move on.
Okay, hello everyone. Because my supervisor Yan can't attend the conference, so I will share our studies with you. Previous presentations discussed a lot about the effects of the aerosol on the convection. Here I will talk about the impacts of convection on the trace gases. So next slide, please. Here is the background. As you can see, the strong updraft can transport the air pollutants near the ground to the upper level, and some will be scavenged. Especially the lightning will produce some noise, which will affect the photolysis of ozone. Because of the lower temperature in the upper troposphere, it can stay for longer and affect the ozone all around the world. However, previous studies mostly focus on the America or ocean regions. So we decided to use different kinds of data like the model simulation, ozone sounds, and satellite to investigate the convections over China, especially the polluted regions. Next slide, please. Okay, we successfully captured 2 different kinds of convection in the last 2 years. The first one is the air mass convection, and the second one is the score line. As you can see, the blue line is the trajectory of the ozone sound before the convection, and the red lines are after the convection or during the convection, especially the 2021. And you can see the ozone sound was swallowed by the convection. It can produce a very valuable observation for our studies. So by comparing the ozone profiles before the convection and after the convection, we can get the convection effects on ozone clearly. Next slide, please. The dashed lines are date before the convection, and the solid lines are after or during the convection. As indicated by the red rectangle, you can see the ozone and the water vapor mixing ratios are higher after the convection. Besides, both cases saw the similar two-valley shape of ozone profile, but they exist in different heat levels. By comparing the green solid line with the red solid line, the green solid line is the Wolfram simulations, and the ozone profile simulated, and the red line is the observed ozone profile after the convection. Although the Wolfram can underestimate the ozone concentration, but the general shape of the ozone profile are quite well. So we decided to use the Wolfram simulations to discuss the possible causes of the ozone change. So there are three kinds of possible causes. The first one is the transport, the second one is the chemistry, and the last one is the ozone directly produced by lightning. We will not discuss the last one because that's quite uncertain based on the previous studies. So next slide, please. In the first column, we divide the life cycle of the two convections into three stages. The green line is the initiation stage, and the orange line is the development, and the blue line, the last one, is dissipation. As you can see, for the 2019 case, the upper tropospheric ozone decreased first and then increased again. But for the 2020 case, the upper tropospheric ozone increases continuously. It can be explained by the second column, the ozone cross section. For the 2019 case, the low ozone concentration air is transported by a strong updraft, and the strong updraft can cause the higher ozone concentration air near the tropopause downward into the upper troposphere. But for the 2020 case, the convection just transports the higher ozone concentration from nearby to the observation station. And for the last column, we divide the contributions into two kinds, the advection and the chemistry. And interestingly, the advection dominates the ozone change for the first case, but the chemistry is the dominance for the 2020 case. Note that the last column is for the convective period, and for the next slide, we will discuss the life cycle. So next slide, please. So for the life cycle, we calculate the contributions from advection and chemistry. As you can see, the chemistry tendency occupies more than 80% for both cases. So we need to take care of the chemistry. And for the lightning logs, we can compare the off-cam simulations with lightning logs and without lightning logs. As you can see, for the 2019 case, the lightning logs can decrease the ozone sharply. But for the 2020 case, it's not obvious because the lightning occurred far away from the station. So next slide, please. As the lightning logs are quite important for the ozone concentration, we want to use the satellite called TripleOmi to calculate the lightning logs production efficiency, which can be used in the model, like the global model or the regional chemistry model. Firstly, we resample the off-cam simulations to the pixels of TripleOmi satellite, and then we develop a new algorithm to get the lightning logs production directly. And finally, we get the production efficiency is around 88 mole per flash, but the uncertainty is quite large because of the satellite and model limits. So next slide, please.
2 minutes.
Okay. Then we discuss the effects of lightning nodes on the official triple-ohmic unknown 2 product. The official unknown 2 product is the unknown 2 column density from the ground to the triple pulse. Briefly, if the defined delta AMF chop is negative, then it indicates that the official unknown 2 product is underestimated, just like the blue rectangles shown in the figure. We divide the region into 3 kinds. The first one is the active lightning region, which means that the lightning happened just before the triple-ohmic overpasses, and the last 2 kinds are the downwind of active lightning or the dissipated lightning regions. So for the active lightning region, the official unknown 2 is underestimated and is opposite for the other 2 kinds of region. So we suggest the triple-ohmic official needs to update their algorithm for the unknown 2 product because they haven't considered that into their product. So next slide, please. Here is a summary. The red circles shows the date we used, like the regional off-cam model, and the ozone sounds, the lightning date, and radar date. And then we got the red one, which is the phenomena, the higher ozone and the water vapor mixing ratios. And the blue ones is the satellite results. We can use the satellite to calculate the lightning nodes production efficiencies, and we indicate that the triple-ohmic official products need to consider the lightning nodes in detail. Next slide, please. Okay, if you are interested in the source code of the off-cam model with the lightning date assimilation or the retrieval algorithm of the triple-ohmic, you can just search online for the GitHub. Just type GitHub and my name or just the name of the repository. Okay, thank you. That's all.
Okay, thank you. We do have time for a question or two. You can use the raise hand tool if you have a question or put it in the chat. I'll just make a comment that we're for ACPC, we're talking about how we'll use Tracer to answer some of these questions. And I think this work on transport of ozone and the relationships between lightning and ozone, Tracer will provide a great data set to be able to look at some of these things in more detail. And maybe that's something we should be including in some of our simulation work.
Yes, thanks. Appreciate a lot. Well, we just have the ozone sound data. We don't have the observation like the airplane. It's very hard to do it in China. Yeah. And I see a question, to test what? Mandate to test.
I think he's asking if you have used any data to test your model result.
Oh, okay. We didn't show in the presentation, but we use the radar observations to test our model results.
Okay, great. Thank you very much. I think we should move along. Jingyi, if you can please introduce the next speaker.
Yeah, the next speaker is Ross Herbert from the University of Oxford, and he will present the work, the isolating large-scale smoke impacts on cloud and precipitation with the convection permitting resolution. So Ross, please take it away.
Thank you very much. So I'm going to basically talk about some modeling work we've been doing. We're basically looking at the smoke impact on clouds and precipitation over the Amazon. So to acknowledge Philip and Guy as co-authors this work. Next slide, please. So we commonly observe smoke interacting with convection, but I think there's still surprisingly lack of literature on this. So I think as a community, we still need to understand how ACI and ARI kind of effects manifest on these large spatial and temporal scales has been highlighted by several presentations this week. So this is one thing we're looking at. Next slide, please. So we're using the ICON model in a regional configuration, and we're setting this up over the Amazon rainforest during the dry season when we have a lot of smoke. It's a very large domain. We have high resolution, and these are 8-day simulations. So they're very big simulations, and we can really kind of use this to understand the large scale interaction with aerosol. And so, for instance, we have stratiform, we have shallow convection, deep convection, and we have mesoscale systems that kind of initiate and propagate throughout this 8-day simulation. So it's a really good way to test these ideas. Next slide, please. Okay, so we prescribe the aerosol and the cloud droplet number concentration using Bjorn Stevens' MAC-SP plume model. And this plume model gives us vertical and horizontal distribution of AOD, as you can see in the top panels here. And then we use field observations of cloud droplet number concentration as a function of AOD, just to get a representative CDNC distribution, which you can see in the bottom right there. And so this kind of gives us a reasonable approximation for what we see, what we observe over the Amazon in terms of the spatial distribution and kind of the magnitude as well. Next slide, please. So we've got a number of different experiments to isolate the different smoke effects. So first of all, the microphysics effect, we just perturbed the cloud droplet number concentration in the cloud microphysics scheme. Next, we isolate the radiative impact just by putting the aerosol in the radiation scheme. And then we can decompose this further by removing this in situ heating and just isolating the reduced surface shortwave flux. So we have this surface cooling. And then we have a total effect where we turn on everything. Next slide, please. So these are results from looking at the updraft speeds in the domain. So we have the time series on the x-axis, and then the y-axis is the maximum updraft speed in each grid box. And then each vertical profile is basically looking at the distribution of updraft speeds in the domain at that time. So for the control here, we see these maximum updraft speeds in the afternoon of each day. And so this is the convective initiation, so the convection popping off and then developing throughout the diurnal cycle, which we can see each day. So the response, blues show the suppression of wind speed, updraft speeds, and red shows enhancement. So the response to microphysics, we find a suppression at these low updraft speeds, and then potentially some enhancement at higher updraft speeds, which could point towards convective invigoration, but it's not massively consistent throughout the simulation. So it might be playing a secondary role or just not so important in these simulations. Next is the rad-scat. So this is when we have the surface cooling. And what we now see is this really pronounced suppression of convection in the afternoon. So we have the updraft speeds are really suppressed throughout all of these updraft speeds. And we see this every single day as well. So it's really showing that the convective initiation is really being suppressed. When we add the in situ heating from the smoke layer, we still get this suppressed convection in the afternoon, but then we get this enhancement overnight. So what the radiation is doing is producing this pronounced diurnal cycle in the convection response. And now if we look at the total response, we see it mimics the radiation quite closely. So it's really showing that the large-scale dynamical response in our domain is largely driven by the radiation. Next slide, please. So now precipitation rate, again, 8-day time series on the x-axis. Now we're looking at the y-axis, the rain rate intensity across the domain. So top plot here is control. This black line is the domain mean precipitation rate. So we see some spin up at the beginning of the simulation, but then we find this kind of consistent diurnal cycle. We have deep convection, we have lots of precipitation. That's what this peak is basically producing. So onto the responses, blue means suppression again, red enhancement. So with the microphysics, as we increase the number of droplet concentration, we suppress the warm rain process. So we find this suppression of precipitation across much of the domain, but it's kind of, it's centered, it's predominantly at these lower precipitation rates. So under kind of 1 millimeter per hour, which is this dash line here. For the rad-scat, So this is the surface cooling. As we suppress the convection, we suppress the high intensity precipitation rates associated with the deep convection, which is what you can see in this diurnal cycle here. And so these are higher precipitation rates than the microphysics. And this line here is the cumulative precipitation. And you can see throughout in the domain, and you can see throughout the simulation this consistent decrease. When we have the in situ heating from the radiation, we then get enhanced precipitation overnight, again, kind of along the lines of this enhanced convection. And so the radiation is producing this nice diurnal cycle in convection and precipitation. So then for the total response, even though in the updraft speeds we saw it was dominated by the radiation, now we see that the precipitation is it's a combination of both microphysics and radiation, which points towards different regimes being impacted by the different processes, which is, this is the kind of thing that you can only see if you look at a large scale where you've got lots of different clouds interacting. Next slide, please.
2 minutes.
Thanks. So back one, please. Right, so this is the domain mean liquid and ice response, liquid water path on the top, ice water path on the bottom. Red line radiation, blue line microphysics, black line total. So what I want to point towards here, so liquid water path, first of all, very different response from the microphysics and radiation. Over the first 2 days, the black line is a kind of additive effect from both processes, whereas after 2 days, the black line follows the red line and it's mainly dominated by this radiation. So it's really showing this really important temporal sensitivity to the kind of interaction of the clouds and the aerosol. Now with the ice water path, we see for both processes strong increase in ice water path, and this is additive throughout the entire simulation. So different properties of the clouds are being kind of interacting differently with the processes. Next slide, please. So this is the relative response. I'm just going to focus on this top plot here. This is the domain mean effective radiative forcing, top of atmosphere. Red is in long wave, blue short wave, black net. So few things we can really nicely see. First of all, the red line, the long wave, increases throughout the simulation. And this is the ice water path response that's driving this. And it's really showing this strong sensitivity to the time scale. So, and similarly with the short wave, we see it changes throughout the simulation. And so we can see that, so day one is very different to day 4. So strong sensitivity to temporal scale and a very strong sensitivity to the ice water path. But if you look down the right here, this is a similar study last year by Liu et al. 2020 using WRF, and in their simulations, they don't see this ice water path response. So the different ways the model treats ice or convection responses really impacts the overall response. Next slide, please. So quickly, I've shown that the simulations produce this really strong, pronounced diurnal cycle in the cloud properties. So potentially we should be able to see this in satellite. So this is using 18 years of Terra and Aqua data from over the Amazon. And I'm just showing the liquid water path. So Terra goes over in the morning, Aqua goes in the afternoon. So we can kind of get an idea of the diurnal cycle. And this is just using all that data. This shows liquid water path increases with AOD in the morning, but in the afternoon we get a slight increase at first, but then we have this suppression. And this nicely matches up with what Tian Meng was showing in the convective cloud cover. So there's a lot more work to do on this, but it's very interesting that we can use this. And then last slide, please. So just to summarize, we've used this large scale, this large domain to really identify kind of how ACI and ARI kind of manifests in different regimes, showing this really strong sensitivity to the time scale, the temporal scale, the longevity of these aerosol perturbations. The high cloud cover is really important and is clearly very sensitive in these simulations. But as other talks this week have shown, we really need to understand these timescales more importantly and use geostationary or Terra versus Aqua observations. So thanks very much.
Okay, thank you, Ross. I think in the interest of time, we're going to have to move along, but I do see there's a couple questions in the chat to your talk, if you can go ahead and answer those in there. And now we're going to move on to the lightning talks. For these, I'll just chime in. They should be about 2 minutes long with time for questions, but I'll chime in at 3 minutes if you're getting close to using up all the time. Jingyi, can you please introduce the next speaker?
Yeah, the first speaker in short session is the Yanda Zhang from the State University of New York at the Albany. So Yanda, please go ahead. Yanda, can you hear me?
Oh yeah, can you hear me now?
Yeah, great.
Okay. My study is mainly about the impact of dust aerosol on summertime convective cloud and precipitation. And first of all, I would like to thank all the co-authors for their contribution to this research. As we all know that the mineral dust is one of the most abundant aerosol species in the atmosphere, which is indicated by previous studies to have impacts on cloud and precipitations, serving as season and as nuclear particles. So in this study, we use a Wolf model with Morrison and SBM microphysics schemes coupled with the DeMont 2015 in marine freezing parameterizations to study the effect of dust on summertime convective cloud and precipitation. The dust profiles simulated by the GeoScam API model are used as dust initial and boundary conditions in these Wolf simulations. We can see from the result that the numerical experiment indicates that the long-range transported dust with relatively low number concentration can have notable impacts on cloud and precipitations. The result shows that with the dust effect, Wolf runs with both bulk and bin schemes predicted stronger precipitation with improved rainfall patterns, intensity, and development. The next slide, please. Okay. So we can also see from the simulation results that dust is also proved to have impact on cloud properties, such as ice water content, liquid water content, cloud top height, particle size distributions. And in this study, the results show that dust can directly enhance cloud ice formation through a heterogeneous freezing process. And dust can also increase the latent heating rate through enhanced condensation and deposition process, leading to the intensified convection. We can also see from the result that from the vertical profiles, that comparing to the Morrison scheme, SBM scheme predicted a weaker increase in latent heating and updraft in the middle altitude, but simulated stronger enhancement at upper levels. The results indicate that this difference of dust effect simulated by bulk and spectral bin schemes are caused partially by the saturation adjustment used in the bulk schemes. Okay, that's all. Thanks.
Okay, we have time for a quick question for Yanda. Does anyone have a question? Okay, thank you. Then why don't we go ahead and move along?
Our next speaker is Bhupendra Raut from the India Institute of Tropical Meteorology. Bhupendra, please go ahead.
Thank you. Hello, everyone. Today, I'm going to show you how drop size distributions are classified in the monsoon over the surface, and then how radar structure of the reflectivity and the other polarimetric parameters looks like for those drop size distributions. Usually what happens is that we look at the rainfall and then classify rainfall into convective and stratiform, and then we look at the drop size distributions. In this case, what we did is we classified the drop size distribution using k-means algorithm. Next slide, please. And we found out that there should be approximately 5 or 6 classes from the 2 years of monsoon data. And these are the solid lines that you can see. I don't think you can see the pointers, but the solid line are the centroids of the classes. And the shaded area is the interquartile range for all the 5 drop size distribution classes. And there are 5 such classes, but today I'm only going to present the 2 for the lack of time. And you can see there are 2 most different drop size distribution that are observed at the surface. Is the one that is DSD2, which is shown in purple color, and that has large droplets. It has a very broad drop size distribution. It is associated with heavy rainfall, and its total membership in the cluster is 3.7%, which is very less. And it does not occur for more than 10 minutes most of the time. So that suggests that this is coming from the patchy, short-term, very heavy convective rainfall. And then the 5th drop size distribution is having very small droplets. It occurs like 72% of the time, has very low rain rate, and is associated with the widespread rainfall with the small drop size distribution. What we did is, for the consecutive occurrences of these drop size distribution clusters, if they are occurring for consecutively 4 to 5 minutes, then we looked at the radar scan, and during that radar window, whatever cluster was occurring more often, we assigned that radar scan to that particular clusters, and then we plotted the CFADs. Next slide, please. So I'm showing these 2 clusters only, and you can see the first CFAD that you can see is the drop size distribution 2 for the reflectivity. The second column shows KDP, and the third column shows ZDR. You can see there is a very strong and notable difference between these 2 clusters in terms of the vertical reflectivity profile. The drop size distribution 2 is associated with a very tall and very strong convective clouds. It also has a lot of ice processes that can be indicated by the high reflectivity values between above the 4 kilometer, which is approximately the melting layer during monsoon. And there are moderate KDP values and the increasing ZDR values above the 4 kilometer, which shows that ice processes are strong in these clouds. And at the lower level, it has very nice increasing reflectivity profile till the surface, also associated with the increasing KDP profile, which suggests that the drops are growing and they are in large number. These kind of profiles are usually observed over the ocean, as reported by Liu and Zupser. But these profiles are also observed over the monsoonic region, over the semi-arid region, as you might have seen some of the yesterday's CFADs from the radar reflectivity, that the reflectivity tend to decrease as the drops are coming near the surface. But in this case, we saw that in all the convective drop size distributions over monsoon region, the reflectivity increases, and it is usually associated with the increasing ZDR. This particular cluster also has a very strong KDP, suggesting large number of huge amount of liquid water content. As opposed to that, this is the 5, which is the stratiform, which is associated with stratiform rain, has a flat, constant reflectivity from melting layer, which suggests that the drops are not growing and that the size control processes are not dominating in this region. It also has a lower liquid water content, and ZDR increment is just a little bit, which shows that there are some big drops because ZDR is sensitive to some drops, and you can see that in the tail of that the drop size distribution, there are some drops that are bigger in size. And so this shows that the bigger drops are produced by the taller convective cloud in the monsoon region, although in the semi-arid region, the more taller and more stronger cloud, they're supposed to have reducing reflectivity. So what we did, we also checked how the MRR drop size distribution is looking like for these 2 clusters. Next slide, please.
Pedro, if you could wrap up, you're over time already.
Yes, this is the last one.
Okay.
So in the MRR, we did the same thing, and this is the first one is the associated drop size distribution profile in vertical for the drop size for the convection, and the second is for the stratiform. And as you can see, there is a large number of small droplets. The peak of small droplets is in the lowest 2 kilometer, which is the reason that the other drops that are falling from this region, they are getting they are having a lot of collision and coalescence, and these larger drops are increasing at the expense of smaller drops, which is not happening in the stratiform rain, because of which you have this increasing reflectivity in the drop size distributions of the convective rain, but not in the reflectivity of the stratiform rain. We have done this for all the fly clusters, and the paper is now under review. Thank you.
Okay, thank you very much. If you have further questions, please put them in the chat. And Jingyi, let's move to the next speaker.
Okay, our next speaker is the Chandan Sarangi from the India Institute of Technology. Chandan, please go ahead.
Yeah, thank you. Today I will highlight about one of my finding in does aerosol has a role in changing the cloud structure or distribution? When I say structure, I mean the ratio of towers, convective towers to anvil. This is what I tried to examine over the Indian summer monsoon region. Yeah, next. Next, please. Yeah, so just to start with, like given overview, how does cloud distribution looks during Indian summer monsoon? The right hand side figure is a NASA satellite figure. You can see river Ganges also flowing in the bottom of the figure. So it's from the monsoon region, and you can see simultaneously both towers, small cumulus, big towers, as well as anvils, they encompass the whole region. So if you think of a region, let's say 50 kilometer by 50 kilometer, you will find both simultaneously present and also in a column. So in the left hand side, to check this, we have done a radio sound campaign. It's a high frequency. When I say high frequency, every 2 hours we release radio sounds, and we try to see how does the vertical distribution changes. In this left side figure, you are seeing the bottom, the x-axis is the time of the radio sound loss, so it's the time, and y-axis is altitude, and we have divided the various cloud layers we identified, and you can see that in most of the places the blue layers are the tower clouds, and then you find them a lot of anvils are also present. So hence both these are important in context to our region. Next, please. And with that, next, please.
Can you see it now? I guess there is a delay.
Yes.
Okay, great.
Okay, so first we used MODIS satellite to see how does the ratio of these anvils and towers change or are associated with changes in AOD measurements. So the left-hand side figure shows the ISMR box. So this is the box where most of Indian rainfall happens during monsoon, and we have taken the entire box and for each 1 degree by 1 degree grid, we have used level 2 data to identify the number of pixels having anvils and then number of pixels having towers. And we have presented the whole scatter plot in the right-hand side. And what we are seeing are the whole sample is divided into 50 boxes of 2 percentile each and co-located with the MODIS AOD. So as we see with increase in aerosols, it seems that the distribution of anvils are much higher compared to the enhancement in towers, or in other sense, the tower to anvil ratio is decreasing. So more anvils are associated with higher aerosol conditions. Next. To better understand this now, we are doing a high resolution simulation at 3 kilometers. So we have taken the entire ISMR domain, and we have taken one monsoon season, July to August 2011, and we are saving the data for every hour. So you can imagine a 3 kilometer resolution every hour for 60 days. We are bringing all those clouds which are getting simulated and plotting them to see the distribution. And we have done 2 simulations, one low aerosol and one high aerosol scenario. So panel A shows the low aerosol scenario and panel B shows the high aerosol scenario. And I want you to focus to panel C, which is actually the difference of this. And what we are seeing is, so the y-axis is showing the cloud top height of this set of system of clouds, and the x-axis is showing the cloud thickness. In that sense, when we go to the right end of the panel, these are more representative of the towers, which are like 8 kilometer, 10 kilometer height, and at top they are at 13 to 15 kilometer, the tops lie. And as you move towards the left side of the panel, you have more anvils getting created. So three things are very clear. One, we are getting more towers and anvils as we are increasing the CCN in the domain for a monsoon season. Second is very, and this is very consistent with last 5 years of work over this region. Many of my papers as well as contemporary researchers are being showing that aerosol integration is a key factor during Indian summer monsoon. So we are seeing that the cloud top is increasing. But what is more interesting is we can see that in the low aerosol scenario, most of the clouds were present below 15 kilometer. And as we increase the CCN, the cloud distribution shifts by 1 or 2 kilometer. And at the same time, during monsoon period, we have a lot of easterly jets which are flowing over ISMR. So this increase in cloud top may also interact with those easterly jets, and the shearing effect may be creating a lot of more anvils dynamically. So the belief, so cloud integration is also being is coupling with the easterly shearing effect to create more anvils now compared to a case when the aerosols are less or a cleaner case. Yeah, thank you. This is my.
Okay, thank you very much. If you have further questions, we're going to have to move along, but please put those in the chat. And we have one more of the short presentations.
Our next speaker, Gayatri Kulkarni, is unable to join today. So Sarah will present on behalf of her. So Sarah, please go ahead.
Hello, this is Tara. Actually, Gayatri could not join. I don't know whether I'm audible. Am I audible?
Yes, I can hear you.
Yeah. Okay. So actually, it is our work, and we have also collaboration with UN. So in this particular work, it is currently under revision in atmospheric research. In this particular work, she has considered an idealistic Elias simulation of with varying humidity as well as aerosol number concentration. And the site that we have chosen is over the Indian Peninsula. And basic idea is to look at the precipitation in different aerosol environments, thermodynamic as well as aerosol environments. Next slide, please. So different sensitivity experiments we have done with that, and there is the basis for this experiments are the thermodynamic conditions that we have observed during the northeast monsoon season over the peninsular region. So this is a typical red zone observation, and we have varied the humidity profile in that with plus or minus 20%, and also the aerosol number concentration were varied from 100 to 3000 cc. Next slide, please. So our basic emphasis was looking into the phase fraction and also the precipitation. These are indeed indicating the phase fraction. As you can see, the mixed phase, indeed, we have found that the mixed phase indeed dominating during the moist conditions, especially during the conditions that are having more aerosol concentration, and the precipitation also has been enhanced during the high aerosol, high humidity conditions. Next slide, please. Next, yeah, thank you. And then we have, in this particular work, we have also looked at p-means of different quantities like the supercooled liquid, ice water content, snow water content, etc. And a number of parameters have been systematically evaluated. So we found that there is a significant enhancement in the supercooled liquid in the polluted as well as in the conditions. And also in the ice water content and the snow water content especially had increased in this. And this indeed corroborates with the previous study that is mentioned. We have more ice clouds forming under high polluted environments. So also the precipitation and the next slide, please. Yeah. Okay, so now the combined effect of this moisture and aerosol, we have also looked at with respect to different process rates from the model. So as you know, it gives really an important assessment of which processes are being important here. So the deposition rate, for example, it found to be quite important, and also the aggregation. We have seen that the snow was quite enhanced during this. And then we wanted to investigate the rhyming bit more in detail. So we have also done some sensitivity studies with the Hallett-Mossop process. Next slide, please. I'm not going into very many details of that, but here we can see the size distributions. Basically it is the the continuous lines are where the Hallett-Mossop processes is on, and the dash lines are where Hallett-Mossop is off. And black one is when the clean conditions, and the red are the conditions. So definitely there is a significant impact during the high moisture and the high pollution conditions. But we can see that the number concentration has enhanced, but there was no significant enhancement in the precipitation. Next slide, please. So basically, I want to summarize that what we found in the moist environment, we have low cloud base, deeper clouds, more supercooled liquid, and advanced mixed phase processes, and a high mixed phase fraction and enhancement in the precipitation. While under high CCN environment, with the more humidity, we have higher amount of snow forming, although droplet sizes are small, but it indeed enhances at a higher levels and forms more precipitation. Notice from the HM process sensitivity, we can see that there is increase in the ice crystal number concentration, aggregation and deposition processes, but and also the ice water content, but less impact on the precipitation. So basically we want to give the message that aerosol effects on the cloud phase and precipitation are more significant in the moist environment. Thank you.
Okay, thank you very much, Tara. If folks have further questions for Tara, please put them in the chat. But I think we want to move along. We have about 15 minutes left for discussion, and I'm going to hand it off to Yuan Wang, who's going to be the moderator for our discussion moving forward.
All right, thank you, Mike. Can you hear me?
Yes, we can hear you.
Okay, great. Yeah, we have about 15 minutes instead of 30 minutes, which make my job much easier. So let's see. I saw a lot of interesting discussions in the chat box. So any of you who asked questions want to have some follow-on questions, please raise your hand so we can unmute you. Meanwhile, yeah, I can throw out some questions here. So for the first talk, Tianmeng uses geostationary Himawari clouds, which is quite interesting. So I have a question probably for either Zhenqing or Ralph, like how about aerosol retrieval from a geostationary satellite? And what's the progress there? And I assume the geostationary has coarser resolution compared with polar orbiting satellite. And does that make the collocation between aerosol and the cloud more challenging? So anyone can take this question.
Sure, I can say a few words about that if you want. It's currently an area of research, and the fact that we have these new instruments like ABI and the Himawari Imager open up a lot of possibilities. Most of the work that's been done up to now has been done with single view interpretation, which means you can get a constraint on the optical depth, but you have to make a lot of assumptions about particle properties. And several groups, including ours, have started to look at the possibility of doing things with multi-angle observations, either from several geostationary satellites viewing the same area or from a single geostationary satellite over time. Either way, you get the path length varying, which gives you, and the scattering angle as well, which gives you some additional information. It's an area of current research. The possibilities are considerable. The spatial resolution is not bad at low latitudes, but of course it degrades seriously at high latitudes from the geostationary platforms. So those are the trade-offs at the moment.
Cool. Yeah, it's very interesting to know. Like we can have multi-angle, retrievals from different geostationary satellite. Yeah, that's definitely something interesting. So, any further comments? And so, Tianmeng, are you there? I do have a question. Like, so since your analysis domain is very big, across hundreds of kilometers, you analyze the terrain height. I'm wondering, how about the surface land type? That may also affect your latent heat flux as well, because like the wetland, the forest, and urban surface may have quite different ET, evapotranspiration rate. Would that be a factor as well?
Yeah, I think that would be a factor that needed to be considered. And we just choose a large area just to show some statistical results here. And maybe we can just see the different land types in the future, I think. And yeah, that.
Thanks. Yeah, Zhenqing, you have comments or questions? Yeah. Please unmute yourself.
Yes, Tianmeng, this is her PhD study. So when she started this, we had two things in mind. One is to analyze the topography effect. Another one is try to look at the lifetime effect by taking advantage of the geostationary satellite, so that we can track the convective cell from the beginning to the end. And so we have not reached that goal yet. And for this committee, I just wonder, it's kind of challenging to do really tracking the cell evolution for large data set, just like we did for ensemble analysis that she did. So I wonder if anyone have anything done along this line or any recommendation of what's the best scheme to do tracking of convective cells of cloud. Because lifetime effect of aerosol has been the kind of weakest part of the aerosol effect, partially because we don't have such data to do. Of course, from model simulation, you can get all kinds of things, but from observation, it's a big challenge. So with geospatial satellite, we are able to do in principle if we have a smart enough scheme. So that's just kind of question for the community. To anyone to have a comment or suggestions?
Yeah, I think Zheng Xingpan from Wuhan, is he here? I think he has done such thing with, yeah, and Danny's here, so he's the one to talk about this.
All right. Actually, yesterday we presented an extensive study showing the life cycle from geostationary satellite, and this. And actually we are using two methodologies. One, taking area and following the life cycle of the evolution of the convection there without tracking individual convective cell. And that's what was presented yesterday, with substantial impact of aerosols actually increased by 30% from clean to polluted, increasing the life cycle of the convection itself. Time scales of several hours to more than to up to 3 days for the evolution of the full of the convection cycle. The second approach is tracking the actual individual convective clusters throughout their life cycle. And now we have a student in Wuhan who is doing that, and it seems to be working nicely and reproducing some of the results of the fixed area tracking with some additional insights, and that will be published, I guess, in the next several months also. So these are two methods that appear to be viable, and it is an open path for the community, I believe.
Okay, good.
Yeah, I remember a couple of years ago, there's a study from Rong Fu's group also analyzed MCS lifetime and its sensitivity to aerosols in a PNAS paper a couple of years ago. Okay, good. I saw Guangzhang. You have any comments or questions?
Yes. So far for yesterday and today, I saw a lot of interesting talks on observational and cloud scale modeling results, and but I haven't seen much of discussions on regional versus and global models. And I saw interesting talk from Philip yesterday, and today's talk from Ross on regional scale, but none of the talks so far on global scale, which I know it's hard. And so first we have to understand the process level interaction between aerosols and clouds and convection, and how to get that into the global model is going to be difficult. So I'm wondering to this group as a whole, if there's any plan on how to bring up this global model aspect into this study.
I can make a comment on that. So I know there's a few projects going on to look at kind of global cloud resolving scale simulations. So Bjorn Stevens is currently running a year-long 10-kilometer scale cloud resolving simulation. Now that doesn't include aerosol, but we're hoping to jump on this and do a small, maybe a month worth of simulations where we include this plume model that I showed and a similar kind of methodology. So we can, you know, it's very rough. It's prescribed aerosol, prescribed cloud droplet number concentration, but this, you know, it's a way to potentially head towards global cloud resolving. And then Philip is, I don't think Philip's here, but he's involved in a project called NextGems, which is just, I think it'll be starting in a few months. And this is aimed at, this is global cloud resolving. And I think the idea is to have some kind of stripped down aerosol module included in that. So, you know, maybe in a couple, maybe next year or a couple of years, I think Philip and the group might be able to respond to that a bit more. But I think your comment's completely correct. You know, I think what I was doing is to an extent pushing the limit of what we can do in terms of the scale and the resolution, but it's probably still not enough, I think.
Yeah, Andrew, you want to chime in about NCAR's effort?
Yeah, we're sort of pushing our modeling system in the same direction toward the diamond configurations, but it'll come with sort of the full physics and aerosols. And so we're hoping in the next year to kind of be in the place where at that 4 kilometer scale or so, we might be able to actually run sort of, what we do in the climate model, which is 2-moment microphysics and bulk aerosols. That probably is not going to do the right thing in deep convection, certainly for continental convection, just because we're not going to get the right updrafts. But it'll take some work, but we have subgrid information within that. And so I think, Wong, that, you've actually done some of this already, with the stuff you've done with Xiaoliang and Song in trying to get aerosols and effects in the deep convective cloud. So that's one avenue that's been explored. The other option is to actually try to scale models where we do regional configurations of global models and actually try to do finer resolution to kind of go across these different scales. But I think getting down to the convective scale to get the interactions, as people know, at this sub-kilometer level is going to take a long time with global models. I think it's going to have to be done in a more creative way than just brute force.
Thank you.
So, yeah, Andrew, I have a follow-on question. Like, if you do have like a 4 kilometer global cloud result model, how would you expect the aerosol effect, how the difference can be like a super parameterized model which already take aerosol effect into account, but in a 2-dimensional cloud result model there?
Well, what you would really get is the mesoscale organization that you're not getting in some of the super parameterized models. And you're going to get the long-term evolution and explicit sort of appropriate lifetime of aerosols from emissions through scavenging through deposition that I think you have a hard time with some of the boundary conditions. However, Ross's simulations are really good, sort of attempt to try to get at that. But, the other way we can do this is we can do 1 kilometer around like the Amazon in a global context and kind of still get a lot of those boundary conditions, but try to get, as fine as we can to get the more intense updrafts essentially. But I think the lifetime effects and the evolution is what's going to be different about doing these larger global simulations.
Yeah, I think the varying mesh approaches.
Yeah, the varying mesh would enable us to do more tractable simulations where we could run for a month and you'd still get aerosols like coming into a basin. Right. You'd still get all the processes and you'd still get the right sort of budgets and energetics without having to worry too much about, by the time you do a continent, you sort of have boundary conditions with an ocean, but they are fully interactive. And so I think you can do a lot. And that's probably the more tractable way to look at this problem, is to set it up with finer resolution over regional type areas, but in a full global simulation, so we can do the full aerosol life cycle.
That's cool. I do see a question from Sue for Andrew. What kind of time frame do you envision running the model?
How big's your computer, Sue?
Yeah.
And how much storage do you have?
Yeah, Andrew, I'm hoping you're doing it. I'm just wondering.
Well, you can get time on it. It's closer to you than it is to us.
That's a good point. I'm just wondering how efficient they are. Are we going to be able to run these on monthly timescales or these annual, or just
talk to Dave Randall, because we're pushing it also onto GPU. We're also pushing this whole thing onto GPUs.
Yep.
Yeah, the intent is to get the dynamics and the physics and the aerosols running on GPU enabled systems. And so, this is a long-term 5 to 10 year project. It's essentially our effort to play catch up with sort of where ICON is and some of the other modeling systems in the Met Office, and serve it out to the sort of US-based and global modeling community. But this is sort of why we're going there, is to get the full ability to use all these tools. We're basically bringing WRF and the global model CESM together so that these configurations are kind of possible on the next machines.
Well, that's how,
yeah, Philip says you can just run ICON too.
Yeah,
I'm sure
I see that.
It runs on our system. But ICON, well, yeah, you got to get the aerosol model running in ICON, Philip.
Ross. Okay, we're on it. Yeah, we're basically trying to produce a stripped down version of the ham aerosol module, which can then kind of have these capabilities, some capability of having interactive aerosol on larger domains. Yeah.
Just
So basically,
curiously, is Icon publicly available right now? Anyone
It's
can
available
download
with a
it?
license, but it's possible to get a license.
Okay, cool. Yeah, I saw Jiwen has a question, hands up there. Jiwen, you want to chime in?
Yeah, and yes, I just want to chime in. It's really something we have to be thinking, particularly for CRM community. You know, how we go beyond this regional scale or even local, just local scale. So I would just want to say, you know, there's a few possibilities, and you know, people just discussed. Another thing is from the DOE, the E3SM. We have the screen model, and this model we already run the diamond field campaign. I mean diamond in comparison for the CRM resolution 3 kilometer. But yeah, we don't have aerosol yet. Rather, it's prescribed. So next step, you know, we have Eagles project, which is develop something for high resolution aerosol for the screen. So it's coming. So we'll think about we'll do some aerosol work with that, I think.
All right,
and
thank you. I saw we already over the time. So what's the plan here? Do we want a photo again? The daily photo?
Yeah, sure. We can take a photo, I think.
So who is going to do that?
Mark is good at it. I usually didn't take just do screenshot basically, right?
Yes. Yeah, if everyone could turn their cameras on, and we'll do a quick picture and then take a break.
So Mike, are we done here?
Sorry, there we go. Thank you. Thank you, everyone. We'll come back in about 15 minutes.
Okay, see ya.
Okay, thank you.
Thank you.
So we've got Minnie, I think, is the one who's sharing the slides for this. Is that right?
Yes. Scott,
Awesome.
Minnie should introduce speaker and share slide. Is she there?
I wonder if we've made her a co-host yet.
I think I just did. Now
Oh,
she is.
Great. Excellent.
Jessica is a note taker.
Yeah.
Jessica is there. I saw her from the people list.
Yes, I'm here.
Good.
Wonderful. Thank you so much, Jessica, for agreeing to do this.
And the Minnie is also there. Minnie, can you? Scott, you introduce your take
I do
over
timing.
probably.
I do timing, don't I? So I do the
Yeah. You do
wrapping up.
timing and then
Awesome. But Minnie, are you sharing the slides for the talks? Minnie, are you able to share the slides for the talks? I can do it if needed.
You know what? I'm not sure that we sent Minnie the slides.
I will share the slides and I'm going to share my screen now.
okay.
I just realized we
All right.
But Minnie did not respond. Can she introduce speaker?
Hi, I'm here.
Oh.
Great. How do the slides look? Does that look all right?
Yeah.
Looks great.
Fantastic.
Scott, can you hear me?
I can hear you great, Marcus.
Okay, great. Should I get started?
What time are we at? We've got 1 minute to go, but then Minnie will do the introductions. All right, Minnie, you want to kick us off?
Sure. The first presenter of this session, the second session is Marcus van Leer Walke from NASAGS and Columbia University. And the presentation title is Life Cycle Studies of Convective Updrafts and Microphysics in Variable Aerosol Concentration via Simulated and Observation Polarimetric Radar and Lightning Flash Analysis. Marcus, please take it away.
Okay, thank you for that. I won't repeat the title because it's pretty long. This is work that's being done in close collaboration with Toshimatsui Takeguchi at NASA Goddard, Eric Bruning and Jessica Souza at Texas Tech, and Ann Fridland at NASA GIS. So let's see, next slide. So this is sort of work that was inspired by a pilot study that was led by Ann, where we tracked cells in 2D in the observations and also in some simulations, and basically looking at some of the characteristics. And the hypothesis here is that we can understand these things best if we track their evolution. So, and I know that's very much in line with Tracer. And following these cells, we saw some sort of intriguing differences in the polarimetric and lightning characteristics of some of the storms that we observed. Next slide, please. So the idea is, once again, that we can sort of most coherently interpret the evolution when we track these the cells, and not only sort of at the full cell scale, but also at the thermal scale. So as updraft thermals are evolving in space and time, we want to observe the microphysics that are happening around those thermals. And we think that's probably the best way to do a comparison with the observations, to understand any critical deficiencies in our models, and also sort of microphysical pathways that might modulate the aerosol effects. Next slide. So what we hope to do is first of all sort of expand our observational analysis that was shown in this pilot study. We'd like to do a more thorough analysis of the next rad in Houston. So that's ongoing right now. I'll show some preliminary results of that. And basically, this is what we did for our pilot study. We sort of hand chose a few cells. We want a more statistical and more detailed analysis that includes lightning flash analysis. So that was one thing that we didn't include. We did have a statistical analysis in that paper, but we didn't go into as much depth in the polarimetric variables, and we didn't include the lightning. So that's what we hope to do, and that will hopefully support the Tracer science goals as well, by having a sort of robust analysis of those features. Next slide, please. Yeah, I won't go into this too much, except to say that we're hoping that we can have very high time resolution observations such as these from Tracer, where we can actually observe the evolution of the thermal happening in 3D as it's sort of rising up. So this is from some preliminary data from a 2018 SGP case with the XSAPers, where we did a targeted scanning with sub 2-minute updates on the radar volumes. We're actually able to see this sort of rising thermal in the reflectivity field, at least. Next slide, please. Lightning is also a really good target for this. I think there's an animation there, but I don't see it showing up. Okay. Oops.
No, I don't think we can get animation, sorry.
Okay, no problem. Let me just skip to the next slide then, please. So one of the things about lightning, of course, and the LMA is that there's virtually infinitesimal time resolution. Well, at least with comparison to, say, the radar refresh rates that we get. We can get very detailed time evolution of these features, and depending on the analysis, specifically if you look at the small flashes, so that's that sort of second histogram down, you can sort of see features that are rising in time, possibly associated with these rising thermals. So we have some additional very detailed timescale information there we'd like to leverage. Next slide, please. Okay, and again, let me just skip right past this. Next slide, please. So we also have a strong modeling component where we'll run in sort of forecast mode to support the Tracer IOP, and also in a research mode to really get at detailed, high resolution simulations, 250 to 50 meter resolution. And one thing I'll note here is that we're using a microphysics scheme, the NSSL 2-moment microphysics scheme that has prognostic electrification. So we'll be able to see in the model simulations of what regions are getting charged, as well as a simulation of the discharge. So depending on forecast or research, that'll be done in a sort of less detailed or more detailed way. And we also have a polarimetric forward operator to have a comparison in the radar observational space. I'll say a little bit more about that in a second. Next slide, please.
1 second. Yeah.
Okay, there we go. So this is some details about the NSSL two-moment microphysics. I won't say too much except to show an example of some of the charge fields that we can predict from this. This is one of the ACPC Houston cases down below, and to show that we're able to look at some of that charge structure as well. Next slide, please. So this is basically I guess, spaghetti diagram of all of the processes within this game. And to note that we have aerosol processes in here, this 3-mode condensation nuclei, as well as ice nucleation will be updated as well. Next slide, please. Okay, and here's some details. For example, the DeMott ice nucleation for deposition condensational freezing, and also the parameterization for the droplet nucleation. Next slide, please. Okay, so Toshi's been working really hard on getting Polaris, the radar forward operator, working in line. So this is actually pretty interesting. What it's doing is that as the model time step is running, it is actually calculating the physical scanning of the radar, so that it's basically emulating about as accurately as you could possibly emulate what a radar would see if the model field was the actual cloud field. So this will really allow for a very accurate one-to-one comparison between the model and the observations, sort of perfectly matching the radar scan strategy, as well as an analysis of potential scan strategies that might work or not work for different types of cells. So we're really excited about this. Next slide. This is just an example of some PPI and RHI that we can look at with these. Next slide, please. Okay, this is sort of details of the semi-operational forecasting. I won't go into this. I won't talk about this too much, but please contact me if you're interested in this. Next slide, please. So Jessica Souza has been working very hard at improving the sort of tracking and analysis using TINT, which is now part of TOBAC, to identify and track cells in the Houston region, and also to determine whether they're isolated or not. So looking so far at 2 months, I believe, of data, she's identified a number of cells. And so far, and this is, I'll emphasize that this is highly preliminary, but so far it seems like the sort of golden case of the perfectly isolated cell that we're hoping to find in Tracer tends to be a lot less prevalent than cells that may be isolated at some point in their life cycle, but also may be a part of a multicellular structure at some point. So if we look at images here on the right, and these are supposed to be animations, and I apologize for that, you can see that they can be in sort of more messy conditions. So this does raise the question a little bit of what do we consider isolated when we're considering our tracer targets. We might have to think a little bit carefully about how we determine whether a cell is isolated. If we're looking for something that's perfectly isolated through its entire life cycle, that might be very difficult to find. But sort of loosening that restriction might be an expectation that we need to have. Next slide, please. And then I'll mention also that there's work that Daniel Hernandez-Deckers has led on tracking thermals. So this is sort of the real hope that we can do a comparison between the model and the observations, really on the time and spatial scales of the thermals. And so far what he's noticed is that there are strong microphysical effects of aerosols that may be observable in this thermal scale. that might not be visible in the dynamics, but might be visible, say, in the microphysics, possibly in the lightning, that we'd like to possibly identify. Next slide, please. Okay, so that's about it. We hope to be in service of tracer science, both from the modeling and the observational side. And we're really looking forward to digging more into this sort of long-term analysis of the Houston region to get a real picture of what our targets are most likely to look like. Thank you. That's it.
Thanks, Marcus. I think I'm glad to be here, by the way, at this tracer session. It's exciting. Very nice talk, Marcus. I'm biased. I have a question here. Marcus, what are the main mechanisms of charge separation in your scheme? Collisions between ice hydrometeors?
I believe that's it, but I think if Toshi is here, he could probably answer more definitively.
Yeah, it's unbonding collisions, especially the rhymed particle, so the convective core. Can you hear me?
Yes, we heard you. Thanks, Toshi. Any follow-up on that from Yuan? Or I don't see any other questions here right now either. So I think we're running a little bit behind the official schedule. So maybe we just go to the next talk and discuss more at the end. Am I right about that? Okay.
And Minnie, you may
Yes.
move forward.
Yeah. Next, we have Steve Salibi from Colorado State University. He will present evaluating aerosol indirect effects on convective cells in the MIP models from a joint modeling and radar simulator perspective. Steve, over to you.
Okay, thanks very much, Minnie. So I'd like to acknowledge my collaborators first, Sue Vandenhever, Mariko Wee, Pavlos Kallias, and Peter Marinescu. Next slide, please. So this work is related to our initial project goals for Tracer. We're calling this our pre-Tracer period. So we're looking first to determine predominant microphysical and dynamical processes that impact isolated deep convective cells as a function of aerosol loading and life cycle. And we're initially looking at this by linking the ACPC Houston area RAMS modeling results of convective cells with some radar-derived quantities via a radar simulator and then a cell tracking algorithm. And then we're going to examine aerosol effects on the evolution of hydrometeor characteristics and microphysical processes of convective cells that are tracked by these radar quantities. And then eventually we'll extend this to all the MIP models once we have our analysis methods down pat. And so just as a refresher, our model domain is there on the bottom left, targeted the Houston area. And on the right, it shows our comparative clean and polluted aerosol profiles that we're going to examine. Next slide, please. So this is also just a refresher slide that shows you some of the isolated convection during a particular snapshot in time around 3:30 local for the Houston area. We can see on the left panel, this is low level temperature. We see some cold pools developing associated with some of the cells. And on the right panel, we see low level liquid water showing the raining area. So we can see some of the isolatedness of the convection and also some of the convection that's not quite so isolated that Marcus was alluding to. Next slide, please. So we're using the TOBAC cloud tracking algorithm on the RAM simulations. And Mariko from Stony Brook has been using the RAM simulations run through her cloud resolving model radar simulator or CRSIM for us to do some tracking on. So we initially started looking at this and Mariko ran TOBAC over the derived 40 dBz reflectivity at 2 kilometers, just to give us kind of an initial idea of how well this would work together. And then as a follow-up to potentially isolate weaker cells as well, she ran this over a vertically integrated liquid for reflectivities greater than 0 dBz. So we're kind of examining how the tracking algorithm works differently, but depending on how we sample and track the cells. Next slide, please. So these are histograms of cell duration on the x-axis and then the number of cells on the y-axis. And we have clean tracking from the clean simulations on the left, polluted on the right, with the 40 dBz tracking on top and the vertically integrated liquid tracking on the bottom. And so with these histograms, we notice a couple of different things. First, the VIL tracking identifies many more cells. However, most of those are very short-lived. And that's somewhat expected given that we're going to track weaker cells that kind of form and then die out quickly. But for both tracking methods, there tend to be more identified cells in the clean simulations. And this may be related to the fact that we're tracking on hydrometeor quantities that are impacted by the aerosol loading. Next slide, please. So this is just another way of looking at the cells that we've identified. I'm just showing tracks of some of the longer lived cells here just to declutter the scene a bit. But again, we look at the clean tracks on the left, polluted tracks on the right, the two different tracking mechanisms on the top and the bottom. And we can just see the variety of cells that we get, some very short-lived, some long-lived. So there's quite a bit to look at here and cells to composite over. Next slide, please. Okay, so for the remaining 3 slides, we want to take a look at some cell composites. We started out by looking at some individual cells and realized we need to start compositing these. So what we've done is we've summed up an individual microphysical species and processes focused on the cell centers or the cell cores, and then we've summed up or we've averaged all of the cells to create these cell composites. And then we're looking at these in kind of a time height profile scene. And the time on the x-axis here is a normalized time. So we're looking at cell composites for cells that last anywhere from 30 minutes to 90 minutes and try to normalize the time component and then take a look at how these things vary depending on how we track the cells and then how the aerosol loading varies. So in looking at this example, we've got the cloud water mixing ratio composites over these tracked cells. And if we compare the top 2 panels to the bottom 2, we see with the bottom ones, with the VIL tracking, this includes weaker cells, and we can see that is indicated by generally reduced composite values. So we are picking up more of these weaker cells. And then also, when we compare the left panels to the right panels with aerosol loading, we see that we get increased total cloud water due to aerosol loading present in both sampling methods, though it's perhaps more dramatic in the VIL tracking method, given the possibility that aerosol effects may be fractionally larger for weaker cells. Next slide, please. So the next 2 slides are kind of the meat of what we're looking at right now. So these are also time height profiles of cell composites, and these are just from the VIL tracked cells. So we're looking at the cloud water composite, rainwater, and hail in the clean simulations in the top 3 panels for these time height profiles. And then the bottom 3 are the differences taken as polluted minus clean. So wanted to have one takeaway point kind of from each plot. So we see on the bottom left, we're looking at the difference in cloud water as we have aerosol loading. So we see at the big bright red area, we get a greater total cloud water over most of the cell lifetime, which is generally what we'd expect to see when we have aerosol loading. The bottom middle panel, we see the difference in the rain mixing ratio with aerosol loading. We see an overall reduction in the rain production highlighted in the big blue area between the surface and about 4 kilometers. However, we also see this red band above 3 to 4 kilometers over the course of the simulation that indicates there is some rain being generated aloft, perhaps by a delayed autoconversion process, and also perhaps additional melting of ice contributing toward the end of the simulation.
Steve,
and this is something we'll dig into more. And then in the final lower right panel, the hail composite mixing ratio shows initially delayed hail formation at the very beginning of the cell lifetime, but then the big bright red area in the center of the cell lifetime shows we get an overall increase in hail within these hail core, or within the convective cores. And so we're seeing this potential shift from rainwater to water-coated ice species when we have this aerosol loading. So next slide. Okay, so this is the final detailed slide here. And so here, similar to the previous type of plot, we're looking at the microphysical process rates for the cloud to rain conversion, the rising of cloud water, and then evaporation as 3 interesting microphysical processes. So in the bottom left panel, we see the differences in the rain conversion, cloud to rain conversion due to aerosol loading. We see a net reduction indicated by the blues in the lower levels, and then and generally an upward shift toward rain conversion at a higher altitude, and an overall general reduction in the amount of cloud to rain conversion. And that tends to coincide with what we saw with less rain produced in the previous plot. In the bottom center panel, we see in the bright red area for the riming of cloud water, we see a big increase in riming in the first half of the cell lifetime, and then it kind of shuts down a bit toward the second half. And this kind of agrees with what Ji Wen was showing yesterday, in that while we may not get a large difference in perhaps hail embryo formation, we can get a lot more riming type of growth and perhaps more liquid-coated high-density ice when we add a lot of aerosol. So this is interesting to see that we've got different simulations producing similar types of microphysical results. And then finally, in the bottom right panel, the evaporation fields are pretty interesting. We see that the change due to aerosol loading shows us in the bright red area that we get a lot more evaporation increasing aloft. And this perhaps has to do with greater evaporation along cloud edges associated with a much larger population of smaller drops that are more susceptible to evaporation. We also see that blue area right near the surface during part of the lifetime of the cell that shows reduced evaporation coming from rain. And so with less rain and a change in the droplet distribution, we're reducing the evaporation, which certainly has implications for cold pools. Next slide, please. So to wrap this up, we're generally working toward identifying the most promising radar-based cell tracking criteria and thresholds using the RAMS simulations from the ACPC Houston area runs. And then we're examining cell composites to identify the most prolific aerosol-induced changes and microphysical quantities that could impact radar-based retrievals. And then finally, the radar-based cell tracking strategies are going to be extended to the remainder of the MIP models once we kind of narrow down the best way to look at these processes, and then assess the aerosol impacts in all of these models. Thanks so much.
And we're pretty much at time right now.
Any quick questions? I would just like to clarify, the MIP is the model intercomparison that Sue and I co-led for the pre-campaign?
Yes, that's correct.
ACPC, okay, great, thanks.
Hey Steve, it's Toshi. Can I ask a quick question?
Yes.
Yeah, it's a really cool slide, especially a time height composite between clean and unpolluted. I just got like a weird feeling that time height composite at the time 0, you already got like a peak of the precipitations. So is that due to the still issues in the tobacco coatings?
That, Toshi, that's something we definitely have discussed in some of our group meetings with Pavlos's group. It's tough. That's why we switched from doing the 40 dBz echo tracking to the VIL, trying to capture the earlier cell onset. Because once you track on 40 dBz, you've already got a pretty well-developed cell. So that is a challenge. Something has to be present in order to track it. So we're continuing to experiment with that, but that's definitely a question that's on our minds.
Okay, yeah, our team is trying to do the same thing, so we might get hitting same issues eventually.
Yeah, sounds
Thank
good.
you.
Let's definitely talk about that.
I can't help mentioning, this comes up really when you're out there trying to do this in real time, because after the fact, you can do backward tracking, which is something that Marcus did on both the observations and the model, but it's a unique challenge of Tracer not to be able to do that. Thanks. Nice talk.
Thanks, Anne.
All right, the next presenter is Dia Wang from Brookhaven National Laboratory. She'll give a presentation titled Linking Synoptic Patterns to Cloud Properties and Local Circulations over the Houston's Texas region. Dia, the floor is yours.
Thank you, Minnie, for the introduction. Good morning, everyone. I'm Dia. I'm from Brookhaven National Lab. So first, I'd like to acknowledge my co-authors, Mike Jensen, Scott John Grande, and Minnie Park for their contributions to this work. Next slide, please. So why it's important to look at synoptical patterns and regimes? First of all, of course, we want to be better prepared for the Tracer campaign deployment and also the forecasting activities during the campaign. So one way is to provide climatology guidance on cloud properties and also the probability of sea breeze convection, which is a major target of the Tracer campaign. So another strong motivation to us is that using observations to study aerosol convection interactions has been extremely challenging. So one of the reasons is that isolating the aerosol effects from the effects of other environmental factors is particularly difficult. So defining periods of similar meteorological conditions is a vital step prior to the development of the aerosol convection relationships. In this study, we are going to classify meteorological regimes over the Houston region using machine learning techniques. And eventually, we want to be able to identify regimes that are favorable for sea breeze convection and sea breeze circulation. Next slide, please. For regime classification, we use a self-organizing map, which is an unsupervised machine learning technique. So the SOM gives us a continuous distribution of synoptical regimes rather than simply representing individual clusters. So we applied SOM to 10 years of 700 millibar geopotential height anomalies from ERA5 reanalysis dataset. We only look at the summer month of the year, which is the tracer IOP period. And from the SOM, we get 16 synoptical regimes in total. But on the red panel plot, we only show 4 primary regimes. But keeping in mind that we have a spectrum of transitional states between those primary regimes. So on the red panel plot, the contours are the composite of 700 millibar geopotential heights, and the colors represent anomalies. Red colors are the positive anomalies, and blue colors are the negative anomalies. The most common regimes during the summer month in Houston are the anticyclone regimes, which are the 2 regimes on the left panel. So regime 0 is a westward expansion of the Bermuda High, and regime 12 is a continental anticyclone regime. The other 2 primary regimes are related to the trough activities, which are relatively less common during the summer month in Houston. So regime 3 is a pre-trough pattern, and regime 15 is a post-trough pattern. Next slide, please. So if we were to look at the regime configurations in each month, you will see that their frequencies are quite different. In June, and so these donuts plots show the percentage of each regime in each month. So the red colors represent the anticyclone regimes, and the blue colors are the trough-related regimes. So it's pretty clear that in June and September, Houston region is frequently experiences synoptical introjects, and is 57% of the time in June. But in July and August, you see lots of yellow colors. So it indicates that Houston region is dominated by high pressure systems, either continental or maritime anticyclones, and it's 86% of the time in July. So these synoptical states are much stable in those months, so Houston is frequently influenced by sea breeze circulation and sea breeze convection. Next slide, please. The next step is to project satellite and radar datasets onto each regime to demonstrate the correlations of cloud properties with these patterns. So on the red panel plot, I show 2 examples of potential sea breeze regimes, but we also have those neighboring regimes that are also potential sea breeze patterns. And the colors on the plot represent the percentage of GOES AR brightness temperature lower than 240 Kelvin. And these composites are for 19 UTC. So on the top panel plot, Houston region is within the western part of the Bermuda High. And you see a increase in cloud frequency in the afternoon along the coast due to the significant moisture advection from the Gulf. And on the bottom panel plot is a continental anticyclone regime. So Houston region is dominated by large-scale subsidence with weaker pressure gradient and also lower humidity. So these periods favor strong and frequent sea breeze circulation, but less probability of sea breeze convection. Next slide, please. So we want to further confirm those sea breeze convection regimes that we found earlier. So we plotted the diurnal cycle of convective cell frequency on the top panel plot. So this is just an example of a Bermuda high regime. And the colors on the plot are the similar thing as you saw earlier. So starting from 18 UTC, the panel A, sea breeze convection initiates along the coast and then propagates to the inland in the afternoon. And we also look at the surface wind patterns from the TCEQ measurements. These wind rows are for the tracer Laporte site. So you see a dramatic shift in wind direction and an increase in wind speed, especially from the southeast direction. So this confirms a sea breeze and bay breeze on site at Laporte. So next slide, please. So to summarize these preliminary results, we use a self-organizing map to distinguish 4 primary regimes for the Houston summertime with a spectrum of transitional states between those primary regimes. And in the continental maritime multicyclone regimes, the Houston region is dominated by large-scale subsidence favoring frequent sea breeze convection and sea breeze circulation. In the following study, we are going to apply self-tracking techniques and to further characterize the convective cell properties as a function of regimes. When tracer eventually takes place, we are going to apply SOM to tracer IOP periods and to further explore the relationships in aerosol convection interactions. So that's all I have, and I'm happy to take any questions.
Thank you. Really interesting. Go ahead, Scott.
Let's have plenty of time for questions. We've got 3 minutes for questions.
Okay. We're having a lively discussion here. Go ahead.
Yeah, thank you. Just one thing, I'm very glad in the very last slides, this looks like a density plot. Our tracking the Houston area for many years also shows this very similar density cell location initiation map as this. So yeah, this is very, very encouraging. Just want to point out.
Yes, thank you, Jesse. So yeah, I think there's also a collaboration there if those regime can be used in your studies.
Yeah.
Can you expand on how you define a little bit more cloud versus no cloud? I'm going to go back. You talk here about ghost IR temperature greater than 240 Kelvin at 19 UTC. So you're basically just looking, that helps you determine when there's a convective cloud?
So it's the frequency of the clouds
Okay.
in a particular at a particular location. So 240 Kelvin is just a threshold for deep convective cells, but yeah, it can vary from place to place. So the red colors that you are seeing here is you have almost 30% of the time in these regimes, you will see a deep convective clouds happening at that location.
It's interesting to think about what a 240 Kelvin cell is in terms of its depth, whether these are precipitating or non-precipitating. It's also interesting to look at the sensitivity to that actual temperature there, how robust that is. But it's super. I'm so glad to see you using use of the satellite. Okay, we're at time now, so I'll go back.
Next, Mike Jensen will give a talk on ACPC Deep Convective Roadmap. Mike, please take it away.
Okay, thank you, Minnie. And this is actually going to be a tag team presentation between myself, Ji-Wen, and Scott. I'm talking about the recently drafted roadmap for our ACPC group deep convective activities, really focused on tracer. So this was something tasked to us actually back at the Nanjing meeting, and that thanks to lots of the different developments during tracer, it took a little longer than expected, but we completed this in March, and it's now published on the or posted on the ACPC website. I definitely want to acknowledge, in addition to Ji-Wen and Scott, you see the list of other people who contributed significantly to this roadmap. Next slide, please. Okay, so just to give a quick introduction and background, this builds very much on the success of the 2017 Deep Convective Roadmap. And we've been talking about the past 2 days in particular, lots of the different work that was part of that roadmap, from observational studies, the model to comparison project, which we've heard a lot about, and other modeling studies. I apologize right now, I surely have forgotten some references there, but those were a few of the important work that's come out of this ACPC group. Some major takeaways from those studies were this real need for coordinated measurement and modeling approaches, employing a combination of high resolution, both in time and space, observations of the microphysics, environmental thermodynamics and kinematics, and aerosol chemical and physical properties to understand these interactions between deep convection and aerosol. And these need to be applied with an ensemble of state-of-the-art cloud resolving model simulations, representing a diversity of microphysical representation. So really, there's somewhat of this kitchen sink approach that we need to take to really get at this aerosol deep convection interactions. We need more measurements, more modeling. And this really was the motivation and led to the Tracking Aerosol Convection Interaction Experiment, or TRACER. And I call it TRACER Plus because it's become much bigger than our initial thoughts. Next slide, please. So the roadmap outlines some very overarching science questions. These are very similar to what we had last time. There's still lots of work to do on these. I'm not going to read through these, but it's essentially trying to understand the impacts of the aerosols on the evolution of the microphysical properties within deep convective updrafts, and then the subsequent feedbacks to the cloud shield, the radiation, and the precipitation. Next slide, please. Okay, so of course this led to TRACER, and the roadmap is really focused on the science that we do in preparation for TRACER, during TRACER, and post-TRACER. So we've talked about it a lot, and I've presented this before, but and we'll say a little bit more about it in the next presentation. But TRACER is going to be taking place starting this fall for a period of a year, where we're taking a full suite of in situ and remote sensing measurements of aerosols, clouds, precipitation, and atmospheric state. This is now a combined effort between DOE, NASA, and NSF, of which you'll hear more about in subsequent talks, so I won't say more right now. Next slide, please. Okay, and of course, there's some very specific, beneath the overarching questions that we posed in the roadmap, there's some very specific questions related to the TRACER activities. And again, we've been talking about lots of these over the past couple of days, really understanding the spatial and temporal constraints needed to properly model the convection and the aerosol convection interactions, really understanding the covariability of aerosols in meteorology. It's something that I think we're still going to struggle with. And then, of course, how different aerosols impact the deep convection, including precipitation initiation, total precipitation, and lightning activity. Particularly in the Houston area, the importance of the local circulations, both from the sea breeze and from the urban land surface, is an important component. And then in the end, our goal is not just doing this in high resolution models, but how does that influence the global and regional climate models? Next slide, please. Okay, so just really talking about the plans that are in there. This first slide just talks about the pre-campaign modeling and analysis. And a lot of this is what we just heard about. So I'm repeating a lot of these things, but there's a lot of work still to be done looking at analysis of existing Houston area observations. We've heard a lot already. There's more that can be done there. A continued analysis of the ACPC MIP. And we saw Stephen was showing some examples from that. But I think that's something that we should probably discuss during our discussion time here is what else is being done and what gaps are there and what's being done. It's a treasure trove of data to analyze. Likewise, looking at impacts of different parameterizations in the modeling of convection and urbanization and aerosol impacts on the sea breeze circulation. These are all things that we can do pre-campaign. And with that, if we go to the next slide, I'm going to hand it off to Ji Wen to talk about some of the follow-on activities.
Sorry, muted. Yeah, thanks, Mac. I'm going to present the activities post field campaign or during the field campaign. So here we have some first order data analysis. For example, characterization of aerosol properties. That is the first thing we want to understand: the size distribution, composition, and also CCN activity. The characterization of meteorological conditions. So particularly how the kinematic and thermodynamic properties involving, and they usually change very significantly with time during convection. So those are very important quantities to understand, so to help disentangle the aerosol impact from the covariability with meteorology. Then we want to have a good understanding about the convective properties. For example, the convective core properties, dynamics, macrophysics, and precipitation, lightning. Then from observations, we can examine the correlations of aerosol with meteorology and cloud properties. But we always say, the correlation does not mean causality. So this is from observations. We want to integrate with modeling, which I will discuss a little bit later. Then development is integrated data sets, which means the aerosol, meteorology, convective properties, radar properties, all those are together. Have an integrated data set is very important in both Euler and Lagrange approaches. Then identify the golden cases, which we will use in the next slide, please. So here is some simulations with the golden cases, but some of them actually we can also have the non-total simulation to more fairly, maybe more give us more kind of a statistic modeling understanding. So we can carry out this LES or CIM studies target at the aerosol convection interactions. This particularly focus on extensive evaluation with observations. We talk about the forward simulator, we talk about the cell tracking, and these are very important features we want to apply here to have a really like apple-to-apple comparison between model and also between model observations, and also to understand where is model has problems. We can repeat the ACPC MIP simulations and with this well observed golden cases, so that we can have a better understanding where our models are in terms of compare those observations. Yeah, we also will think about how a model in the comparison study with constrained dynamics and all the physical parameterizations, but only change different macrophysics scheme to look at how aerosol impact would be different, or if the spread is narrowed compared the current SPC and MIP type of work. So this is can be a WMO international cloud modeling work group cases. Then, as Mike just mentioned, we have this open heat effect. Basically, I would call open island effect. No, not open open land effect, because there's lots of other effects, rough race so sea breeze circulation and the aerosol properties, and they're all entangled together. And we want to have a study with this golden cases to look at it. Also forward modeling flooding. This is an area we didn't do much in the past, and I think this is a good opportunity for us to do more. The impact on the cloud lifetime, the radiation. This is really need to integrate with the satellite data in terms of constraining the cloud even stratophone, and then look at how they are corresponding with the aerosol, and then use some model simulations. This can be something that we will think about for next field campaign, because we need additional measurements from field campaign for this kind of study. Then I want to mention all of these activities. We have this tracer modeling group. Sue and I will co-organize together. So the golden case, we will help select the golden cases, also help coordinate some of these activities. I'm sure we cannot coordinate all of them, but try. Next, Scott. You're muted.
I'm muted. We got to pull that trick when we do that in an in-person conference. You kind of get up and start miming. You're muted. So thank you. So yes, so a big part of what we want to do in the Tracer ACPC roadmap is really these Lagrangian studies. And again, to repeat what Mike and Jiwen said, it is really gratifying to see that we're already making such amazing progress now. So create a repository for data, radar, satellite, and model output with the codes for the case study. So basically creating this idea of a cloud atlas, with individually identified cells and events, so that when we come to the analysis, we can actually have very strong coordination, because folks can cross-identify cases and clouds very easily. The application of multiple tracking codes to NextRad observations, folks might have heard, we've actually merged the TINT code base in with TOBAC. That was a direct result of collaborations and conversations here within ACPC, so that we can kind of converge on a similar set of tools. And again, it's fantastic seeing everybody using that open source TOBAC toolkit, and also the work from Jaxi and others on tracks as well. The use of ensemble with perturbing initial conditions and physics at the same time to get an idea of sensitivity and uncertainty quantification, and the comparison and evolution of storm kinematics and microphysics. Basically, one way we can get at comparing models to observations is when we do our MIPS, when we do our modeling studies, to look to see if these models and simulations are accurately representing the cell physics. We can look at the cell life cycles and really make sure that the life cycle of the cells we see in the models are similar to the life cycles of the cells that we look from radar and satellite, using your forward models and so forth. So we can say this is a similar situation. Therefore, we can assume that the the thermal structure and things we can't measure with radar and satellite, but we can model, are more representative of what occurs in nature, more representative of what occurs in nature, because of course it's not directly linked or directly measured. So food for thought. Okay, one thing I want to really highlight here, that Mike, Jiwen, and the whole team is that we really want for there to be good coordination with the analyses from Tracer. So we want to gauge ACPC contributions to Tracer Plus research activities. We want to use ACPC as the coordination mechanism for these studies. So campaign data analysis, identifying golden cases and performing simulations on them, bringing the data to those models, and these, Lagrangian analyses I talked about before. We want to be sure that we're engaging all interested parties. We want this to be very inclusive. We want to really bring anyone who wants to work on this data. But this is the joy of DOE data, is there is no 1-year embargo. As soon as we collect it, that data is out there and ready to use. So we want to engage all interested parties. Are there other questions we should be aiming towards? Is there anything that the people here from ACPC have seen that we really have missed? Is there anything we missed the ball on? Is there anything out of the box we haven't considered? We're still talking about using, CRMs, to a degree, LES. What's the role of machine learning? Is there a role for any DNS modeling here to compare? What's the over the horizon things that we're looking at? Keep in mind, people are still analyzing TWPI data sets today. So we really need to think about, when we're collecting data and doing analyses, what's going to happen in the next decade, and what opportunity, how do we take advantage of the unique umbrella that ACPC provides in bringing in collaborators that might have not been engaged in Tracer before. So I'll hand it back to Anne and everyone for discussion.
Thanks, Scott and all. Danny.
Yeah, this is all great, really. But when we rely so much on the models and we want them to represent the reality as in the best way possible, we should keep in mind that they are only as good as the initialization data. So, and I'm not sure that we put enough emphasis on getting the initialization of the models right by the measurements.
I think that's really good feedback, Danny, and something we need to ensure that ARM is aware of. ARM has a product that it produces that is traditionally used as a forcing data set, or as for both initializing and forcing, that we should, and that's made by Xiaosheng Zi's group out of Livermore. And I think this group should coordinate and collaborate carefully with him to make sure that it's appropriate there. Anne, you've got any thoughts that you've used Xiaosheng stuff?
I do actually. I think this is part of what makes a golden day, because when we're running these regional models, as we think is so important for this type of situation, if we don't have good global reanalysis, or much larger scale model, data for that day, we can just not capture those conditions for reasons that we can see when we go in and compare that initialization data. So I think with this regional variability that we face in the Houston region, that'll be part of choosing a golden day.
It's interesting to think about what would be sufficient and how to determine what is sufficient before we, go in. And maybe, Jiwen and Anne, you need to identify some key stakeholders and really, talk to Xiaosheng's group on what's required. I know they did some bespoke work for cacti, for instance, where topography was so important. They changed to terrain following coordinates, for instance. So what is peculiar about Houston that would require something special?
This is something we could look at in pre-campaign work, actually, I think. And I know that in the work Toshi's group did forecasting for MC3E, it was a remarkable, many events were relatively well accurately forecasted. There would be some timing differences usually there, and big convective events, which could be due to physics actually. But maybe Toshi has something more to say about that if he's here, or other forecasting contributors.
Scott and Ann, but maybe before we do too much more, we have two more short talks that
I'm sorry. Yes, I'm
Right.
going to suggest we skip mine and go to Pavlos first.
Right. Let me just grab these are the short. Got it. There we go. And let me go to Pavlos, you able to see that?
Yes, I can. Thank you.
Rock and roll.
It's supposed to be 2 minutes, just 2 slides. So just to say that the experiment of sea breeze convection aerosol precipitation and environment. ESCAPE is an NSF-funded field campaign partner at this point with the Tracer field campaign aligned once again. They were initially, then they diverted, and now they're back again. I have to say this has been quite a roller coaster for this field campaign. Everything has changed at least twice when it comes to the facilities, but we hope that next year, same days as you can see on the bottom of the box, we're talking about 35 days deployment of the airborne assets and about plus 5 days more for the ground-based. So a very large team has modeling component, has Zach Libo and Sue van der Heever supporting the modeling activities and science we want to do with the ESCAPE. There is 3 very experienced PIs on the aircraft, Greg Raymond and Greg Roberts from Scripps. There is Eric Brewer and Timothy Logan, locals, who are getting support to support both the science, but also help us with the Houston LMA. Actually, the NSF is augmenting and improving the LMA to ensure that's going to be in a good operational status for 2022. And there is some radar PIs, including myself, Mariko, who probably you know has been attending the meeting, Matt Kumjam and Ken Lombardo from Penn State. So quite a big team, very expensive field campaign. The 2 aircrafts we plan to bring, initially we think about one, was supposed to be the King Air, end up being the C-130. And on top of that, the spec Learjet, the new one. And effectively what happened with the delays, we end up augmenting a lot of instrumentation that was supposed to be taking place as is being used right now as we speak in Colorado for the SPECUL campaign, which is basically secondary ice processes in isolated convective clouds, continental convective clouds. So at the end up, we're going to have a superior to what we thought instrumentation and in a good alignment now with the Tracer. The reason why ESCAPE was postponed in 2021, it was moved to 2022, was not the one that you all can suspect, which was COVID. Was rather a very unexpected mechanical issues with the C-130 that were discovered during a heavy inspection that took place over the winter. So I have this presentation, which will be available to all, has more than 15 slides. We can cover all the details if you wanted to know all the probes and all the sensors we have. Let's go to the second slide. You've been talking a lot about the tracking. So a lot of the innovations we're going to do here has to do with the tracking. We are going to implement very different ways of using radars, both on the surveillance and how you track with big radars, but also with all the mobile assets. There will be, primarily when we do tracking, there will be no PPIs, and there will be effectively no traditional tri-Doppler triangles. It will be a very different strategy because we really try to capture the storms and we really try to combine the dynamics from the mobile assets combined with the polarimetric columns from the big precipitation radars. My final thought is that although that sounds very exciting, I want to raise the level, the alert level here, because this is not something we have done before, not just about the tracking, having big mechanical radars and force them to do the things we want to do. We might face unexpected failures. We have to be prepared and we have to build contingency plans. I think coordination to that between ESCAPE, Tracer, and the NASA aircraft radar that will be there is important, just to enable us at least to have at least one solid working radar throughout the period, the IOP, the 4 months. That's it.
Thank you, Mike. Did you want to give your presentation or?
I could do a very quick version of it if you go there quick. I'll skip a few things. So yeah, I'll just give a quick update on the latest developments of planning for the Tracer campaign. If you go to the next slide. And actually this is the motivation. We've heard a lot about this already, so let's skip this one. And just to say a little bit more, so since I presented this last year, a lot has happened, right? COVID came through and changed our schedule. So now really Tracer is kicking off this fall, starting with the NASA campaign that's going to focus on air quality during the month of September. And then DOE starts things in October for a whole year. And now the intensive observation period, where we're going to have most of our observations, including additional measurements of aerosols and clouds from the Atmospheric System Research Program, but also the NSF ESCAPE that Pavlos just talked about, and some other measurements. That's going to happen in the summer of 2022 now instead of 2021. So kind of that whole IOP period has been pushed back a whole year. And that's had some benefits of getting us to be able to prepare some more, and now we're quite coordinated on that. If you go to the next slide, you'll see I'm happy to report that preparation is underway. These are the sites the construction has happened. Actually, it's much further along than this at this point. But this is on the left is the site where the Arm Mobile facility is going to be deployed at an airport in LaPorte. And on the right is where the C-band radar is going to be deployed. If you go to the next slide, I just wanted to say there's still plenty of opportunities to get involved in Tracer if you haven't been up to this point. I invite you to join our science and operations calls. Actually, we have one later today where we talk about the ongoing preparations, and we'll get into the science as the campaign starts. Let me know if you'd like to join that. Ji-Wen mentioned the modeling group. I think a lot of the efforts of ACPC will funnel through that modeling group. So definitely contact Ji-Wen or Sue if you'd like to get involved in that and are not so far. And then there's other activities, weather forecasting, talk to Scott, boundary layer processes. Virendra Gate is leading that science group. There's other subgroup activities looking at the radar stuff, air quality studies, and aerosol processes. And if you just go to the last slide, I just want to acknowledge that I'm representing a huge team of people who are contributing to this. Lots of your names are on there, and I've surely forgotten some there, but this is a huge team effort. And I'll stop there so that we still have some time for discussion.
Mike, you need like those rolling credits you have at the end of the movie.
Yes.
Best boy grip and so.
Thank you, Mike. So we just have a few minutes left officially on the clock here. So are there some high level questions? I know I will just summarize from a lot of the discussion that's happening there. There's a lot of discussion about how people's tracking algorithms differ. And I'm wondering a little bit with our pre-campaign activities, if it's possible for those various groups to adopt one common strategy that's relatively simple. And then we can relate our more specialized strategy to it. So I'm just throwing that question out there.
And or have it into comparison, pick a case so we can understand the differences, I think is really important. And the differences particular assumptions make, whether it's 40 dBz, how you pick what the dBz is, because often you will actually project multiple levels onto the ground, and there are all kinds of other ways to do it as well. I mean, so for instance, one thing Marcus is looking at doing is using the lightning as the tracker and then making the statistics around the lightning. So if you pick a case, then everyone can kind of analyze the same case.
Yeah, but we need to take a case that will start from nothing, that will be able to see the precipitation initiation.
Initiation, exactly.
Case to be considered simultaneously by both everyone, the modeling group and the forecasting group. Or the operations group. I mean, I'm just thinking about how we're going to choose cells in real time as a real concern. So that kind of comes up. There's kind of combined things: tracking and selection in real time. Comments.
I can speak a little bit. Probably we need 2 hours of presentation to tell you what we have done, but we did look extensively to Tobac, Tint, Titan, and MCIT. We end up selecting MCIT modified. We actually had to recode it following the papers from Xiaki. Very well done work, including all the papers, including the last one that he put on the chat. VIL is superior to reflectivity, so that means you have to use all the scans to be able to get that. What we struggle right now is to push as early the detection. That means now we have augmented the satellite in many different levels. Work that Daniel has done also, So this is the part that we're working mostly. So there's a selection and there's a now casting. So obviously we have to do projections, which is based on image processing and figuring out the flow, the horizontal flow. So all this has been done and it's been going on. There's a lot of challenges because from existing radar data, you can only get at certain levels, especially low levels, the wind flow. That doesn't mean that that's how the cell moves in upper levels. In any case, at the end of the day, once we have a selection of cells that are appropriate, isolated to the best of understanding, we capture them early, they look promising. Promising for us, for example, means towards the MF, moving towards the MF, go close to the proximity of where we are, where we have our best sensors. Then there are other geometry calculations. We're not gonna chase a cell which is 80 kilometers far away because probably gonna get like 10-degree elevation, there's gonna be no vertical structure. So we're looking at cells which are very close, but not too close so there's limits. We know what the radar can do. We know the overhead of the time, and we start. This is how many seconds you have. Okay, these are the 50 available cells. Which of them go towards where we are? 10. Out of the 10, which one has the best geometry for us? Meaning we can sample it within 90 seconds, top to bottom, with enough density. Then we stick to that and we execute until the end. In the process, as many of you have noticed, with the climatology, there's a lot of tiles showing up and there's split cells and everything. So the extent we can actually keep that group together, and as long as the geometry works, we track them to a certain extent. So it's not done. The part that we're missing right now is real implementation. There are some challenges with getting the arm radars up to communicate with us. There's some issues with the systems operational status, but we hope to have this accomplished possibly in the September beginning, the test phase. And after that, we can be more complete. We are preparing, and we do have a website with live cases that we're gonna show to all of you. And a cool thing that we do is the following. Because it's the first time we would do that, and an experienced meteorologist could actually have a better judgment of what to do versus an automated system, the PI or the radar science on the ground will have the option to override the system. We will actually be an interface. You will be given the same information that the automated system has, and you will be able to click. And by clicking, you will be able to override everything, and we will following the cell that you want. So hopefully this hybrid operational mode will provide some safety and confidence that we can actually do it in certain times with high confidence of tracking the right clouds.
Thanks, Pavlos. That sounds awesome. And actually what this is making me think is that, that maybe that whole exercise is largely decoupled from our modeling exercise. And what that means is that we can do backward forward tracking in observations and models after the fact with the data set that we end up with using that approach. I see a comment here from Jeff. I wonder if you could speak up, Jeff. I'll read it here. Assessing tracking algorithms is begging for an Aussie. Forward simulate reflectivity from a model simulation so that you have some estimate of truth, be it the vertical velocity field or some estimate. Oops, that's a moving target here for me, or something else that can be used to objectively identify what a cell is. There's an effort at SIMS NSSL to look at cell tracking performance against subjectively determined cell IDs, but that's very time consuming and still subjective. There are also a lot of different algorithms out there. Okay, and he's in a very loud environment, can't speak. Okay, thanks, Jeff.
I think
any other comments? Go ahead.
All of the above is great because we need some real data and real cases because the behavior of cells in an Aussie aren't necessarily always the same as the behavior of cells you see on a radar, unless you've really captured all the dynamics there and cold pull interactions. But I think picking a case, bringing all the data in together, maybe putting them all on the same system so we can all code on there, and having a group like that kind of tracking subgroup to look into. I think because you could even build great teaching materials and cases on that as well. But as you said, Anne, before we actually go in, but there's two separate conversations being had here. We've got tracking for analysis and tracking for like what Pavlos's group is doing, the active tracking. And of course, there's interplay between the two, but because one can certainly learn from the other, but the conversation can get confusing.
So Scott, go ahead. Go ahead, Sue.
I just I think this is a great idea, doing this pre the environment. I think, some of those activities are being done by the different groups now. That's sort of what Steve was talking about earlier. So working on a combined case that ACPC could pick up a pre-tracer where we have the observation tracking element as well as the modeling. You're suggesting both. I'm just trying to understand what we're talking about here. So we would pick a case, run whoever's interested in being a part of the modeling side, have those models run their case. Who's ever doing the observational side, do the observational analysis and then bring everything together. Is that what you're proposing? I'm just trying to be clear of the parallel paths here.
To a degree, and I know you guys have done a lot of work on that already, but I think the case you picked was in the pre-polymetric era of the local 88D, if I remember correctly. Please correct me if I'm not right there, but again, just having
no, I think we had the polarimetric data in our pilot study, and that was one of the days.
Yeah.
So I think we do have the polarimetric data for that. I was going in, my thoughts were going in the same direction, Scott. How would this be different from what we have in hand now?
Yeah.
And otherwise, how is what we have in hand now sufficient to do what you're talking?
That's what I'm trying to understand as to whether or not we're going to do the whole process again, which I'm not sure that's necessarily worth the efforts at this point in time when we have all of these data readily available right now. So
you could use the data you have again for that dress rehearsal idea. We probably just want to bring in some more observational data sets from that period to match up with it. And that I think once you bring that observational data sets in, that will really help us again answer some of those questions that have been brought up about what's the sensitivity of our choices in what we're tracking here.
So is this kind of adding cell tracking, which some of us, which has already been done with some of the MIP simulations? Is that kind of one of the main elements there?
I think only tobacco was used, right? Sue?
Well, in terms of what Steve has done, yeah, but in terms of working with Pavlos, Pavlos and Mariko, Steve, Pavlos, and I have been working on all of this together, and they've looked at a number of other tracking algorithms, as Pavlos just said. So certainly in terms of what Philip and Max have done, they looked at a lot of the tracking across the MIP, but also again with TOBAC. So some has been done with other algorithms, I guess is what I'm wanting to say in terms of what Pavlos has done. But in terms of the MIP, what's been done primarily to date has been with TOBAC. Yeah. So, I mean, there's openings, I guess, to your question, and it just depends on where the group wants to go as to whether or not we want to look at different tracking algorithms or whether we want to dig a whole lot more into advancing the tracking with TOBAC in terms of across the whole MIP. That's what Steve's been doing. Max has done it on as you saw probably in the chat. Max did this with vertical velocity. Steve's been looking into it with Mariko, the different radar variables. We can expand that to it across the MIP and dig into all the radar variables, but also, Pavlos, they've been looking into these other tracking algorithms too, so you can comment on that. Just depends what you want to do, I guess.
I think the most critical thing, if you want to see signatures and probably errors for signatures, is how early can you capture the convective cell? And that's a difficult thing. In the model, you have infinite capabilities, correct? I mean, you can see any reflectivities and you can see any isocontour of liquid water content. In the reality, though, we have to overcome a lot of other scattering mechanisms and other sensitivities issues and artifacts. So I think what I will be very interested to know is how early is important for you to capture in the model something that we will also try to track and directly or with proxies in the observations. That will tell me how much I have to dig into the satellite data effectively. So this exercise could have some interest, but we have seen that the VIL, for example, has an improvement compared to the reflectivity. That's one thing. The other thing is also, once you select a cell, what exactly you do? How do you track statistics there? You average the whole cell, you focus on the maximum value. There's a lot of other parameters that dictate your time dependent of the life cycle statistics. I think that kind of sensitivity study, what are the relationships, what are the ways you formulate the data in a delta T space that gives you the maximum signature is very important. And the question then is that can we actually do something similar to the observations? Having all that in advance will help us a lot because we will know what to go after in the observations.
When it comes to
Go ahead, Seth. We're running over a little in time, and I just want to say that I think this conversation is one that it sounds like we've identified the conversation we want to have, and I wonder if this will be happening in the modeling group. Is that, and also the modeling group is open, right? So any folks who are here today who aren't part of it yet, are welcome to join. Correct, Scott and Mike?
Well, it's Ji-Wen and Sue who are running it, but I think I could probably speak for them and say, yes, if you just email Ji-Wen or Sue, they can get you involved in that modeling group.
Great.
Yeah, also in the next CHES modeling group meeting, this is on our agenda, so we can discuss in more detail there.
Just maybe briefly to throw in, because it's not modeling. We presented last year at ACPC. We didn't present it again, but we have this automatic detection of convective cores from the GOES-R data running that also will be implemented back into TOBAC and should be available. So it's something we could also run for a long time. I mean, we can run the whole US we have run the whole US already for a year, but we could easily run that for that area. Continuously, pretty much. It's a different perspective. It obviously you can detect cells to a certain degree. Once you have a complete anvil over it, you will lose sort of information on the cells. But I think particularly for the early stages, it could be particularly useful.
But in terms of looking at cell life cycles, if we're using forward modeling on the model data, and then we're actually looking at the life cycle from that. So basically comparing profiles of reflectivity versus time, profiles of VIL versus time. This is a big ask, but if the scattering and the issues that Pavlos raised are built in to those forward models, it limits the detectability, insects and stuff like that, and that's a big ask, and I understand that. Then you'll be comparing like versus like. And that's the important thing, is using the observations to constrain the modeling studies, so we know that the models are representative of the life cycle of the cells as we observe them. Then you go to the model data to do your thermal tracking and stuff like that. So forward simulators for what Philip was talking about in terms of ghost cores there, if we're able to link them back, then those observations become the linchpin to constrain the models. And I understand and I fully admit this is a bit of a dream. This is an ideal scenario, and but you know, I think that's a way we can attack this issue.
I'm wondering if we should have a dedicated discussion that isn't just in the modeling group about this tracking thing, because it feels.
As you were talking, I realized we've made a terrible mistake here, because we've got an observations group and a modeling group. We've gone like back to the 80s again. We really need, I think your modeling group, your and Ji-Wen's modeling group needs to be the model observation integration group as well. Because you got to go.
So I actually feel that are things that we want to talk about as modelers together that you do not want to sit through. And so I do think it would be helpful for us to have a joint discussion. I vote for that, but maybe that's something that comes out of this discussion, to periodically come together around that specific topic potentially.
So Anne, as Ji-Wen said earlier, I mean, this is actually the next, it's on our agenda for the next meeting for the modeling group. And maybe we should open that up and let's make it a broad tracer, pre-tracer model ops tracking meeting. So we can all come together, get on the same page and see where we need to go. Take into account Pavlos's very good, points that he's raised. Also what we need from the modeling perspective in terms of the really tough problems of initiation. Let's bring everybody together and let's chat. So
wonderful. Is there anything we've missed here? I think that sounds fantastic. I see a lot of thumbs up. We're running over a little now. Is there anything we've missed here at that level, or any final comments? All right.
Wait, how exciting!
This has been great. All right.
So maybe I could to close us. Maybe I could just say thank you to all the speakers, the organizers. Thank you to Andrew Gettleman and the NCAR folks for hosting us on Zoom the last couple of days. It's run flawlessly. and it's been another great meeting. I think maybe for final closing, Danny, do you have anything you want to say to wrap things up?
Well, just that it has been a great ACPC meeting in which we are getting very close to fulfill our vision. Actually, we are doing that, not close. We are actually doing that. And everybody, we have our work cut to us. We feel that we are not closing it, but we are just getting to, we are stopping this session to get really out to work. That's great. Thank you all. So the meeting is closed. Thank you all.
Thank you.